So I welcome you all to the one-day workshop on 5G networks. We have today with us Dr. Saptarshi Chaudhari. The topic of today's webinar is Layer 2 and Layer 3 protocol and algorithms for OpenRAN based 5G base station. Before proceeding for the session, I would like to introduce our expert speaker for today. Dr. Saptarshi Chaudhari is presently the head of the Radio Access Network System Engineering and L1 Department of Redisys Corporation. Dr. Saptarshi Chaudhari obtained his double bachelor's from the University of Calcutta. He obtained his Bachelor of Science with a physics major from University of Calcutta and did his BTech in Electronics and Communication Engineering from Institute of Radio Physics and Electronics, University of Calcutta. Later, he completed his MTech from the same in the field of radio wireless communication and PhD from IIIT Bangalore. Dr. Saptarshi Chaudhari has 26 years of extensive working in the wireless communication domain, started working in cellular industry from year 1996 onwards in GSM base station and worked to date in all the flavors of GPRS, 3G and CDMA 2000, 4G and 5G base stations. Currently, he is focused on 5G product algorithm research and beyond, base station architecture and design. He has filed 130 plus patent applications across multiple countries, and he has 37 granted US patents and 3 granted European patents with him. He has authored 18 plus international peer-reviewed conferences and journal papers, and he holds the IEEE Senior Membership and Fellow of IEETB position, along with XCOM membership in IEEE ComSoc. He is the recipient of Best Electronics Engineer 2022 from the Institution of Engineers India. We welcome you, sir. Thank you for being today here, and the floor is open for you now.
Okay, thank you, Asta ma'am, actually, and good morning, everybody. It's an honor to be back with IIIT COMET Foundation. Thank you for inviting me here. And to all the participants, I think we have divided into 2 sessions here. One is the pre-lunch and post-lunch. So pre-lunch will cover most of the stuff actually. Post-lunch, maybe some spillover from the pre-lunch, we may go to the post-lunch. The materials is little diverse in nature because we are talking about radio access, and that too one aspect of the product actually, or product of the system. So it will take little time. I'll try to be as lucid as possible with a lot of diagrams in nature. Only caveat is I cannot disclose the algorithms the way that has been implemented. So maybe you can ask questions, I can verbally try to ask it, but I'll try to pose the major things as a part of my questionnaires that from you as a researcher or as a practitioner will come to know that how complex designs that goes in the base station point of view. Okay, so let me first share my screen and let me know. Is it viewable?
Yes, sir. It is very good.
It's ready to go.
Fine. Right, ready to go, sir.
Okay, so what I did here is that my topic I'm trying to restrict today as a layer 2 and layer 3 actually. So, and that too is open base station actually, OpenRAN base station. So we'll try to define what is layer 2, layer 3, and before that, the way that I put my agenda is that I'll go over to the basic requirements of the 5G network deployment. Why I took this topic of the first point is that, see, though we say we are 5G, but the actual definition that is given by IMT is still very broad, very extended actually. So we are yet to catch up to the full requirement of the 5G defined by IMT actually. So we'll try to see that what is the global vision of the 5G that it talks about. And remember, 5G is now moving towards 5G advanced actually, okay. So we are in the stage where the 5G, the base products, the base research has been done, and we are moving slowly to meet and catch up the actual requirement of the 5G. Similarly, if you have been following it up in the 4G days, so we had 4G, then came 4G advanced. Similar, the path is also they are following that. They are trying to deploy the 5G as the base requirement, a subset of the overall IMT, and then they're coming up with the more advanced requirements to catch up with IMT's final one. The second part is the network deployment actually, because network deployment, what happens normally, any standard gives you an holistic big picture actually. So it doesn't talks about that how the products means has to be shaped up. Means you must have heard of the small cells, femto cells. A lot of this small products, large product, medium products get devised to meet the operator's demand actually, because it's not viable for any operator to every time put a macro base stations that in the tower top of our rooftops and to give a complete quality of service to the end-to-end actually. So what they try to see is that wherever they find coverage, hole capacity, hotspots, demands are there, they try to deploy a subset or a form factor, a lesser form factor from the macro. So we'll see that how these form factors affect actually, because obviously when you become like, if it is a femto type of deployment in your home, we don't need a lot of these other big features that the 5G demands actually. So we'll go over to it. And we'll try to see the end-to-end protocol blocks, and some of the call flow I'll try to put it in the last actually. And since the topic is layer 2, layer 3, I'll try to be brief in layer 1, because many other lectures are in the layer 1, but here I'll try to brief it out. Why? Because when we talk about layer 2, it is just above the layer 1. So when we try to do cross-optimized algorithms, a lot of these layer 2 algorithms are dependent, and functionality also depends that how layer 1 behaves. So I'll touch upon the main concept of the layer 1, not getting into the algorithms and other stuff. So that will help us to crystallize then the session 2 of it, that we get into the layer 2 part of it. So this is the very heavy part of it, layer 2 part, because a lot of concepts that goes in the layer 2 base station, and its associated protocols and associated algorithms actually. We'll see and try to uncover the complexities one by one. And then we'll move on to the layer 3 block actually. I try to keep it a little simpler view actually, because layer 3 is top of the sitting top of layer 2 and layer 1 actually. So it is a kind of a big entity that controls the complete holistic control plane of the base station actually. So we'll uncover the basic building blocks, its protocol, and we'll see that how the layer 3 algorithms get devised actually. And then we'll end of the session, we'll try to make an end-to-end flow, because I hope you're able to understand the layer 1, some concept, then layer 2 depth, layer 3 depth, and try to put together that when you switch on your mobiles, how things goes on actually, okay? So that's the way I'll try to make it up. I'll try to draw it as much as possible whenever you have any problem. So that way we'll make it more interactive as much as possible. So let me start with the first slide here actually. This is what the IMT 2020 vision of the 5G looks like. You might have seen this slide n number of times. So I don't want to get into nitty-gritty of it, but there are certain important aspects that I want to bring it forward actually, because that is where we as a researcher and as the product designer, we have to cater to actually. Now, when we started, if you see the evolution, the way the 5G was being planned actually. So we were seeing the experience of the 4G, and 4G was catered to sort of single requirement to all the services that the 4G wants to demand from it actually. So, but what happened to the 5G is that there were the demand that came growing actually. So if you see the tagline of the 4G, we called mobile broadband actually. So that is where the exact broadband aspect of from the experiencing from the device started coming up actually. So the broadband demand was further enhanced actually. So if you see the 5G's base requirement was how to enhance what 4G's broadband demand was actually. So they've tried to focus on that my data rate in the 4G was okay, but what will be the ideal data rate that the 5G should cater to actually? So we started defining, or IMT started defining the peak data rate and then the user experience data rate actually. So if you see the peak from the base station in the downlink direction, downlink means from the base station to the device, they were trying to envisage a number called 20 gigabit per second actually. And so it's a pretty big number actually, because if you see the broadband, and we are talking in the air interface level from the base station to the device, 20 gig per second, we want to experience it out, just like experiencing Ethernet type of speed, though Ethernet is leaps and bounds, it moves in a bigger numbers. But this is what the vision actually. So in the downlink, they expect the base station in the peak level should transmit at 20 gig and in the uplink 10 gig actually. And on an average, and the user means the device, if you start purchasing from the brands, we will be capable of doing a downlink of 100 Mbps or 50 Mbps. So you can imagine the speed in which we are talking about, where 2.5 Mbps has now been talked about as 100 Mbps, because we can configure our system with 100 Mbps, a pretty big speed number we are talking about, though in the interface. A lot of caveats are there, because when we try to give these numbers, there are some idealistic conditions that we want to put forward and test it out. In the real world, if you see the user experiencing the real world, it may not be up to the 100 Mbps, or base station may not pick it up to 200 Gbps actually. Now, other ones that we are trying to focus it on. So, well, just keep this mind in your mind actually, these requirements. You don't have to make sure these numbers. But what happened is that as we progress, when you say 5G, as we are progressing it, we are trying to meet these numbers as much as possible. So it is, if the answer is that, do I have met these numbers? The answer is no, actually. So when we'll meet it, so that's where the standard is moving, bits and bytes actually, that what we call as release 15, 16, 17 has already been in place actually. So the end goal is that how to meet the end numbers what IMT has defined, and what the 3GPP or the standard body tried to see that release to release where I am in meeting these numbers. Now, if you see the spectral efficiency, this is the most concerning part, because this is where the operator starts seeing his revenue actually, because what spectrum he buys and what throughput he tries to give it to you, the more the spectral efficiency, you can see it, like for every hertz, we are trying to give 30 bits per second actually. So more the spectral efficiency, it means that more transmission, more data bits is getting exchanged actually, both in uplink and downlink. And he starts monitoring your bytes and he starts billing you actually. So the demand was that operator is that we have seen the spectral efficiency in the 4G. So we expect a little better spectral efficiency so that the revenue of the operator also goes up. So they started defining what is the peak spectral efficiency that they want to see it, and what is the 5 percentile. This is where the cell edge, because when we talk about the network coverage, you will see that how we divide the cell center, mid center, cell edge type of scenario. And we are talking about the 5 percentile users whose spectral efficiency is not as low, but as numbers as 0.12 to 0.3 bits per second per hertz actually. So these numbers that we need to meet to ensure that by any means, by any deployment conditions, we have to go towards this number actually. So other one is the traffic density actually. So this is where the capacity we are seeing it. It is, if you see per meter square, this is the what the average traffic bits that we are expecting actually. It's a quite large number we are talking about, because this gives you the feel that how you're aggregating your mobiles in a square meter of area actually, and how much of speed that they are demanding on average actually. The latency is another big aspect, though we'll talk about the next slide, that user plane latency, the control plane. The user plane typically, which means that how your packets are entering to the network's first edge of the internet. That is nothing but what we call as a packet core, and getting delivered to your device actually. So how's the user plane latency? How the signaling plane, that in colloquially we call as a control plane, that what is the control plane latency that we wanted to see from this network. And we try to define connection density actually. So for the massive IoT users, they try to figure it out. The energy efficiency, another big stuff that they all bother to actually, because remember, if you try to give this number of peak every time, means in the loaded conditions, obviously there are a lot of energy that will be burnt actually. So they are also a concern that how to make your sleep state of the device, how you control it, what is the ideal based on your traffic pattern. So this is a regular optimization of the parameters that keeps on happening while seeing the key performance values of the network actually. So this is one important aspect we have to see, that how the sleep ratio, you have to devise it out actually. And it shouldn't happen that you make the device sleep but there is a packet that is waiting to be transferred, because we have to wake that user up from the sleep mode and then get it delivered actually. So all those things has to be planned properly so that we are able to deliver the throughput, because remember, it is not, it is aggregated of all the throughput that the base station is looking, because base station controls all the device. Okay, that's the way we have to see, that we cannot make him sleep or make the device sleep, so that we are not able to meet the numbers. The other aspect that came out to be is the reliability actually. Now, remember, if you have seen from the 2G, 3G, 4G, and all this stuff, actually, you'll see that in the 2G times, it was mostly the circuit switching has been planned in your transport network. Actually, that was the basis of the 2G transport. It means that how you get connected between the base station, to the switching centers and all the stuff. Now, what happened is that when we started moving to the packet switching domain, actually, packet switch network, when we started basically, when we started adapting the IP aspect of it, actually, that is nothing but your ITF specification started getting into the 3GPP specification as its base transport. So when we say IP network, it is nothing but the TCP, UDP connection, oriented connection, less, or HTTP type of multi-homings type of scenario. So these are your transport mechanisms 3GPP started taking into account and started dropping the circuit switching network actually. So moment you start coming to the IP network, there is obviously, it is not been devised for a delay sensitive and it's not devised as a reliability. So to make it reliable, your cost of the IP will go down, actually, will go up actually. Okay, that's a major factor they are concerning about. But when that till 4G, we had to live with it actually, because it may not be a reliable to do precision controlled transmission and reception actually, because it's not reliable actually. You cannot ensure that at a critical moment your packet is not received or your telemetric data is lost. A lot of things that is being seen in the 4G. So 4G was not meant for it, though we have tried to put some of the use cases on the 4G, but it failed actually. So when the 5G started rolling it out, or when the conceptualization started happening, one major part started to think is reliability actually. So reliability on a packet switch network. So how to do it actually, what to be done actually. So this is what the standards we're talking about. But remember, standards is a messaging guideline actually, okay? But who implements the things of the reliability is the algorithms part actually. So those things is a critical part. But their demand started coming in the 5G because of certain application we'll see in the next, and you all know, we'll talk about. So how to make it more reliable, for which application it is more reliable, we are talking about. Okay. And the mobility is another big aspect actually. So if you have followed the 4G, we took the mobility till theoretical mobility till 360 kilometers per hour, actually, the speed. Now we are talking about the mobility definition that will go up to 500 kilometers per hour. Actually. So it is a pretty big leap jump from the 4G's mobility. Means the users may cross the cells and do a handover at the rate of 500 kilometers with this user speed actually. So it has a big condition associated with it, that when you go with this high speed and the channel is not favorable to do certain transmission and reception actually. So how to deal with it? What are the mechanisms to do it? So we'll talk about those mechanisms as we progress, actually keeping in mind this high mobility. And the bandwidth, the minimum bandwidth, if you see in the 4G, we kept it at some number, but in 5G, we straight away one single carrier of 100 megahertz channel bandwidth. So if you see, this is the broad numbers that the IMT is trying to devise, keeping in mind, this slide you might have seen it many times, that we started devising these requirements into the applications in which the 5G has to concentrate upon. Actually. Now, this is the first time that happened in 5G, where it was more application-driven standardization approach, actually. So it is not like you build a standard and try to put the application, then you find that the application is not giving the right quality of service from the network, and your experiencing of that network is not that efficient or not that good, actually. So this time what happened is that they are trying to bring forward the application in mind, and they thought that, okay, the first application, we have to enhance the broadband experience actually. So this is the prime focus part of it. And they started saying that, okay, I'll start getting into this reliability and low latency services actually. So this is where they kept in mind that this network should be made in such a way that it has to be ultra reliable in nature actually, and able to deal with low latency application. It means that you cannot ensure the packet to be queued in your network up to a certain duration if the service demands URLCC actually. So by any means, this packet has to go out from the network to the device, and also in a reliable manner, and it shouldn't be queued. So it means that what changes that the system has to bring, the radio access has to bring forward so that it doesn't unnecessarily get queued in the system actually. So then the last point we are trying to work upon now, what stage we are now in the 5G. So more or less we are trying to roll out the product. And if you have seen in India also, the 5G rollout has been the auction has been completed by July-August timeframe, and all the major operators in India are into the deployment phase, and some of the cities already 5G services has been switched on actually for the MBB part of it. So that's the stage we are talking about, and that's the first rollout of the 5G you have been experiencing, and you'll be buying i5G phones. You may see the 5G network wherever they have put up the base station. You can see the throughput, you can measure your throughput, you can experience the 5G. And you'll see that it is now not the coverage has not laid out across the pan India. So it will take a year and a half for any operator to complete the rollout, do the drive test, and make one by one the sites as operational. So what you will experience is the enhanced broadband. But do we experience this type of throughput peak? The answer is no. We are not geared up at this point of time. But you will see a decent speed from your device actually, and you can see and experience most of your application, high throughput applications. So you'll see the next phase where you'll see the URLCC. Some aspect of the URLCC will be deployed actually. And now the operators are doing the thorough testing to it in the lab and some in the field, that how the reliability, how the low latency application are getting experienced. But it is right to be deployed today. The answer is no. It is not to the shape that it will deploy. It will take some more time, some more testing to be done, so where URLCC will be given back to the users like us actually. The massive machine-to-machine, massive machine type of communication, yes, it's a third level of deployment that we'll see years to come actually. Okay, yeah, we are not geared up because we are yet to handle this high density planning in the network. And then once the URLCC is being deployed, then we'll concentrate more from the MMTC type of deployment conditions actually. Now, why I brought this slide is here to tell you that these are the three top level use case driven 5G applications. So we have to think forward as a researcher, as a developer, as an inventor, that how things are moving actually, where to focus on actually, what to be done actually, what needs the standard or our algorithms has to be devised to handle these end-to-end use cases at what level, because this use cases again is a top level statement actually. Now within that statement, you will see when we will try to categorize the quality of service within the broadband, also see how we try to do the categorization. It's not like a network when he deals with it. Not every users are wants 100 Mbps. Some users may want 5 Mbps of the service. Some user may still wants to do a voice communication. So is that not the broadband? No, we don't say a broadband. We are talking about a pipe of a throughput pipe of 100 or throughput pipe of 20 gig from the base station point of view. Now within the pipe, we'll try to uncover what happens actually, because it is a user who controls and demands the service. So it's not that every time we open a pipe like Ethernet pipe and in our broadband DSL, and you start experiencing it. It obviously our traffic pattern, user pattern, mobility pattern, everything changes. That's where the cellular communication is very dynamic in nature. Vis-a-vis if you think of your desktop DSL connection. So if you try to compare here, the biggest thing that you miss it out is the mobility. Normally with your laptop, you do whatever the mobile does it. But what happens to it? Actually, you are in constant move actually. So you take your call, you are in move, suddenly you try to secure your WhatsApp application, suddenly a video gets streamed from your YouTube, suddenly you start getting a call in a voice call actually. So it is very dynamic in nature actually. So with the mobility coming into play, and we are talking in the wireless level, and you know now that how the wireless as a transmitter, channel, and the receiver, these three entities has to work in tandem to give you the experience of this use case. It's pretty complex. We'll uncover that complexity. So this is what I try to make a one quick comparison actually, like you have experienced 4G, all we have experienced the devices that what we have. Now when the 5G is coming out, the first thing is that the subcarrier spacing, what we call actually, okay, so there was a constant subcarrier spacing, but in the 5G, you'll see a lot of flexibility 5G is bringing it out. You know, why this flexibility? Remember that previous slide, because of the applications it has to deal with it actually. So it has tried to put it in the spectrum point of view, in the gigahertz, 6 gigahertz, what we call a sub 6 gigahertz. And we talk about beyond sub 6 gigahertz type of spectrum actually. So if you see the subcarrier is your lowest element that carries your user informations actually. Okay, the symbol information in the physical layer terms, if you talk about at the MAC layer, we talk on the packet level actually. So we form a packet in the MAC. But the packet concept doesn't go in the physical layer system actually, because this packet has to be segmented and it has to be channel coded, modulated, all the principles will go on actually. Now we talk about the minimum granularity in the OFDM, and remember our base is OFDM. So each of the subcarriers of the OFDM, what is the carrier bandwidth that we're talking about actually, and the flexibility that 5G is giving. Based on the application need, he has made 15K kilohertz or 30 kilohertz or 60 kilohertz. So like that, he has tried to space it out, the subcarriers in that level actually. Now the channel bandwidth, this is where the broadband aspect starts coming out actually, where we are talking about the channel bandwidth rolling from up to 100 megahertz per carrier basis. So if you have 2 carriers, you multiply this 2 with 200 meg actually. 3 carriers, 300 meg. That's where the broadband aspect will go up, because more carrier you add, you get more resource to transmit your informations quickly. Okay. Efficient, not efficient for the base station, different, but at least theoretically we will able to pump more throughput from the cell to the users and all this. Now aggregating the carrier up to 16 carriers, we can aggregate actually. So 16 carriers of 100 meg theoretically is a pretty big bandwidth we are talking about actually. Though we are not able to reach to this numbers, we are still at 3 carriers system and all that stuff. So we'll go into this numbers, but we are talking about the channel bandwidth of 100 megahertz actually. So if you see this frame structure, radio frame structure, it has this is the base essential pattern where we keep it the radio frame, because if you've seen from the cellular, from 3G, 4G, 5G, the radio frame is the important elements for our governing our principle. So everything we honor based on the 10 millisecond, and then we start dividing into the subframe slots and everything actually. So if you see the slot actually, that is the minimum granularity of the physical layer for making his symbol packing actually, means OFDM symbol packing. So that has reduced up to 0.125 actually. Okay, so which subcarrier you are trying to work, we have gone down to this level of 0.125 actually, but in 4G it is pretty static actually. Okay, so the channel coding technique has been enhanced. So till 4G we used to have the turbo and the convolution, but here we started putting the LDPC and the polar coding actually. So we kept the OFDM as our base principle of transmission actually. But if you see that the uplink, remember in the 4G we have the DFT spread actually, that aspect of it, and that gives more reliability in the uplink single layer transmission and write SNR to transmit. But here if you see a change that 5G brought in, that he kept the CPU OFDM in the uplink itself. Now why they have brought it, this condition is in the waveform is like this. Suppose you are in a best of cell coverage, best of SNR actually, and you want to do a multi-layer transmission in the uplink. Okay, so that the DFT spread is not been devised to handle multi-layer. It's not meant for it. So then they started saying that the way I'm seeing my downlink throughput to go up, and we also have the CPU FDM type of thing to handle the uplink throughput. Remember the numbers we are talking about. We have to go to 10 gig in the uplink cell throughput that we have to handle to it. So you need to bring forward the CPU FDM at the right favorable condition. We may spark off the multi-layer transmission using CPU FDM. That's the way you can able to achieve the high throughput system. And today, if you get amazed that the phones are coming up with this channel bandwidth support of 100 megahertz, you can think of how the hardware revolution has happened, the RF technology, that we are able to start experiencing the phones with 100 megahertz actually. Okay, now only the pitfall that we are yet to experience is that battery life. So that is the other part, but at least you should appreciate the technology in which we are moving, where the phone today are coming up with 100 megahertz of the support bandwidth actually. So the other aspect of the MIMO transmission technology actually. So here we have brought in a huge improvement here in the MIMO actually with respect to the multi-layer transmission, with respect to the massive MIMO multi-user transmission. So it is a huge improvement that we are trying to bring forward, that today when you are trying to multiplex and experience the multi-user MIMO aspect of it, we are able to transmit 16 layers actually, and that is a pretty formidable numbers actually from the base station point of view. Now, are we into that? Yes, we are going to that. We'll talk about the slide of the massive MIMO a little bit. So we'll see that what are the implications when you're trying to bring forward the multi-user MIMO transmission aspect of it. The HARC code book, the code block segmentation has been brought actually. So initially we used to do a transfer block. Transfer block we'll talk about in the MAC level actually, that how when we exchange a packet, when I say a packet, now in the 3GPP term we call as a transfer block actually. So this blocks is been given to the physical layer actually. Now physical layer used to do the segmentation and do the channel coding. Now we further divided into the code blocks actually to more granularize it out, and we can able to track the HARC per of those segments of the code blocks, so that unnecessary a big transfer block, if we get an error, we don't want to retransmit that big transfer block actually from the physical layer. So these techniques has brought into more faster way of communication actually, because HARC is a retransmission slower mechanism, because if you get into HARC and if the network is been configured to retransmit say 2 times, 4 times, 8 times, so it means that it slows down actually, because it slows down, it eats up the resources of the base station just to ensure that your transfer block is successfully being received by the UE and vice versa. So it is a costly effort in the network, and not to get into the HARC at all actually. But as a wireless, we cannot negate it out. We have to live with HARC actually. So the carrier frequency we are talking about, this is the state in which we are moving, like down below to 600, going up to 28 gigahertz is the millimeter wave is already been deployed actually. So up the carriers, we are moving up and up actually, slowly, steadily actually. So because this is where we are in the range of the gigahertz 28, we are into the millimeter wave transmission technology. It has its own challenge. It has its own way of handling the system and all the stuff. So this you can see now, it is some similar, but what 5G has brought in is enhanced of every stuff that you see in the 4G that has been brought in. It has been looked upon every row item by item, and bring forward the changes, keeping in mind that this 5G has to support the diverse application use cases based on those 3 buckets actually. Okay, now this is another slide that the standard talks about actually. Now, when we say a 5G deployment actually, now this is the idea that how complex the network will be actually. Now, just the way the network get deployed is not like the one core network or one base station actually. Okay, so the network is very much complex than this diagram is showing about, because multiple elements of these things get devised actually. Okay, let us try to understand the deployment part itself. So what if you want to deploy on a 5G network, what do you need actually from if you are an operator? You need a base stations actually. So obviously this base station you'll be buying from the vendors actually. And also you need the core networks elements actually. So whether it's access, mobility, the session, the user plane functions, and a lot of these core network functions, you have to buy it from the vendors. So you bought this elements actually from the vendors, and you have your coverage map, and you start deploying the base stations into those coverage map to give you coverage, and start the way that the device will become. As a user, we have to buy this device, and your network now get rolled out. So when you say network getting rolled out, it is the multiple elements of the core network, multiple base station giving you the coverage actually. Okay, so now you can imagine that the deployment is not small actually, cost wise, equipment wise, connectivity wise. Now, why connectivity? Connectivity means that when we see that, okay, wireless is between this mobile and the base station, but we tend to ignore what happens to the back of the network of the base station. Means the southbound, if you take this base station, the south of the base station is your device. But what is the north of the base station is your access core network elements actually. Now, how we connect actually means the base station getting connected. Obviously, I talked about we connect using the IP network. So what are the components of the IP network for connectivity? We need to buy the routers, we need to buy the switches, we need to buy the optical equipments. Now, how many actually? So depends on what is the throughput that we want to experience in the backhaul actually. Okay. So this is another big deployment that it's not that when we say 5G, we try to concentrate between device and the base station. But as a network operator, they are also been concerned about that how I give a SDN connection, how I do how many routers I need to hop between the base station to the network, whether I want to use how big is this length of this optical fiber if I want to do the optical Ethernet connection. So these are another big entity that the operator talks about. Okay. Now, if you see the way the standard is not talking about, suppose you buy a base station. So what is there inside this base station actually? Now that is where the standard what talks about with respect to the protocols actually. Now this is the first time I'm putting this word called the protocol actually. So the protocol, what is that protocol means actually? So protocol is a way we try to, one element of this network talks to his peer entity actually. Okay. Now suppose let us understand that if you have a mobile phone, within that, it will have its hardware, it will have its modem, it will have its application processor, and a lot of things are there. Okay, but if you see the communication aspect of it, when this mobile wants to communicate with a 5G in place, so obviously the communication protocol is 5G actually. Now the way the communication, it's not ad hoc actually. You cannot go unless there is a constraint or mechanism with which you have to communicate. Then only a mobile can talk to a base station of a 5G base station. Means the 5G phone with its right protocol in place has to talk to the 5G base station in the wireless part of it. Now, how to talk, what are the messages has to be defined is being governed by the standard actually. So you cannot randomly pick up the message here and there. There is a sequence in which you have to make your software to write that protocol. And then only you can talk actually with its peer entity residing somewhere in the network. Okay, let's see that from the device point of view. Suppose EV is the user equipment. So this device, when we try to have it, so there are basic elements, or we divide into the main protocol angles actually. So protocols with respect to the, okay, let's start with the lowest part of it, the physical layer protocol actually. Now, this is where exactly the 5G wireless keeps in play actually. So you have the physical layer that is governed by the OFDM technology aspect of it. Top of that, you have the medium access control, you have the radio link control, you have the packet data PDCP part of it, you have the RRC radio resource control, and you have the non-access stratum. So this is a pretty much names that we are familiar with, more or less 3 generations of our protocol stack itself. Now, stack means that each of this block, when I talk about, has its peer entity residing somewhere in the network actually. Okay, so it means that a non-access stratum, it has its own messaging, own parameters to deal with it, and it has been told that this is your subset of the application, you have to deal with it. So that's the way we make a block, and where its peer entity is residing is in the AMF here. So it means that this part of the protocol is his peer entity is not residing in the base station, it is transparent to the base station, and it been there in the AMF part of it, in the access and mobility functions of the core network actually. So what it does, we'll talk about that aspect of it. But since, let's go to the down below actually. So down below is where we say the radio resource control that is there in my user equipment and is there in my RRC in the G node V actually. So this arrow to arrow becomes peer to peer actually. So whatever you send the packet of RRC, so the other RRC here in the base station and vice versa, they are expecting a request response type of scenario actually. So they expect that if you want to get a service, if you want to set something, you have to tell from this RRC to this RRC. We'll see the use cases when we get into the RRC protocol. And vis-a-vis from this protocol, if the base station want to communicate back to the UE, it has its own RRC protocol layer that will capture and do the necessary action. Similarly, the PDCP, similarly the RRCs, the MAC and the PHY actually. So everybody has its own standard specification document, and we have to read the document to understand that what is the messaging that is expected between these two elements actually. So pretty much if you have these two protocol stack in place, then a device can talk to a base station up to an RRC. But when you talk about non-access stratum, this packet is transparently forwarded to the AMF via this NG interface. And when it lands up to the AMF, it will do its own action based on the AMF protocol document actually. So this is the way the protocol is been segregated actually. Okay. Now, if you just see here, so up to the base station, that is fine. Now, if you see this connection, this is what we call as the interface specification with the AMF actually. So when the base stations wants to talk to the core network, it has its own interface specification called NG app actually. So the standard document of NG app will tell you that what are the messaging that is required to set up a connection between base station to the core network, and follow on actually means what you have to do when you receive what message, what scenario from the base station, what AMF will take an action. All the stuff is well governed with a call for. And in the last slide, we'll do that the connection and build up the story of this protocol. But everywhere, this blocks has a document, and as per the document, you have to write your software, you have to write your state machine to ensure that they are all working in tandem. Because the biggest thing is that the synchronization, it's not a time synchronization, it's the way that we call as a message synchronization, in the sense, if you send some message, the other person or the other entity is in the right state to receive your message and act on your message. Okay. So if it is not in the right state, he will discard the message. So you know that what the discard means. It means that you are not able to communicate to the other entity in the right way. So all your further down below processing stops actually. So this is very important that the protocol entities here has to be in the right state to accept the right message from your other entity actually. Else it will be just getting discarded actually. So we talked about NG app. So this is where the base stations talk to the core network with its own element of the messaging part, and that has its transport mechanism called SCTP actually. So it goes over the IP and its own data link and physical layer actually. The physical layer maybe Ethernet, maybe optical Ethernet, whatever. So it is not based on the WebDM. Now here is a catch. Here is that the catch here is that this data link and this MAC, this can be this physical layer can be replaced with link actually. Okay. So standard wireless link means what actually? So if I say that, okay, can I connect with a Wi-Fi? The answer is pretty yes. If you have the link budget between the base station to the entity called the core network, and if you put one Wi-Fi radio point to point, you can still do a communication. Yes, that can be done. You can do with another spec of 3GPP that is coming called IAB to do this kind of a connection, or the backhaul with a millimeter wave. Yes, you can do it. So varieties of ways they have kept it open, that it's not necessary that you have to ensure that you have to do your optical connectivity or the non-optical ways of doing it. You can still go ahead and do it actually. So they kept it open deliberately, but what they want is that these two mechanisms has to be on your any data link, any physical layer. Okay, that's the reason I kept it little open statement called data link and physical layer. So you can do with Wi-Fi, you can do with any other mechanism you want, provided it has its own data link and physical layer, and you can able to do a point-to-point connectivity. So now you can imagine that the question starts coming. The complexity here is that do this base station has to have only one master called core network? The answer is no. You can have multiple masters. It can connect to the packet core. And this base station, does it want to connect to only single mobile? The answer is no. So this base station, up to the capacity limit of its hardware and its RF, it can communicate to multiple such mobiles in its coverage area. So this is where it's a multi-connectivity problem starts developing actually, okay? Because more you start crisscrossing, the network becomes a quite a big mesh network starts happening in this part of the backhaul of this connection mechanism actually. So we have to deal with this connection mechanism in an efficient manner. And this connection also doesn't restrict, if you think of the base station point of view, it doesn't tell that you have to only connect to the core network. You can straight away connect to another base station also. So it means that we are open to connect to another base station if I want to do a handover and other stuff. So it may happen that in some scenario, this link is not there. I can have to have an handover between facilitated by the core network, or if I have a connection between these two base stations, this XN interface I talked about will facilitate my doing my handover. So you can see the connection mechanism, how complex, and this is where the operator spend time and his effort to ensure that which base station to base station I have to connect, which base station need to connect to which packet core 1 or packet core 2. All this is part of his operator planning the network actually. Okay. And plus these elements are in multi-folds actually. You have many such, and it is, if I want to give a figure of these numbers, it pretty much it goes into hundreds and thousands of or 100,000 means lakhs of the base stations getting into the system, and in tens of the core network in the network. It's a very costly deployment mechanism we are talking about from the operator point of view. So this is what the segment domain we call the 5G core, 5GC actually we call actually this whole part. And this is the RAN actually part, or radio access, or the base stations, whatever we say. Now, the next slide that we want to go for is called the HETnet deployment. And this HETnet comes, I talked about that it defines me the form factor of my base station. So suppose if I say my form factor is a massive MIMO, outdoor small cell, indoor distributed antenna deployment, or a metro cell macro base stations. So, or a simple radio that is connected via an optical fiber, while my base station whole thing sits in my edge cloud or the central cloud. Anything can happen as an operator who wish to deploy his operator environment. So moment he sees that, okay, in some place, I want to only deploy the remote radio head or only the radio, and my processing of my baseband or my layer 1, layer 2, upper 5 to layer 3 protocols are in my edge cloud, it can happen. He may say that, okay, be flexible enough. Don't say that I bring it a single box base station that will fit to all my deployment criteria of this nature. He may also say that, okay, in a building coverage, I want to distribute my the radiating elements, antennas here. Okay, maybe in a tunnel or in elements, and he can aggregate at one point, and with his radio remote head, he'll control and make sure that the whole entity is processed in a cloud environment itself. So here you can see that it is a DAS or distributed antenna system getting deployed. It's outdoor or indoor, doesn't matter to the operator. But what he needs from this slide, it talks about is the flexibility. Flexibility means you can break your base station at any point you like actually. Okay, it may not be random. Okay, so but he expects the flexibility because he wants to get some benefit from a startup who are been great into radio design actually, and maybe another vendor who are great in his layer 2, layer 3 protocols algorithm. So he's expect that, okay, I'll bring two vendors here rather than a one vendor. I'll make two vendors. So this type of lot of this decision happens with respect to the form factor of the base station, the cost of the deployment, working with the different startups or different companies who has their skills in one type of the system. Anything can happen in this, the deployment criteria. Now, what happens if you bring multi-vendors? Obviously, the interworking is the challenge actually, because each vendors, each products, what chip or processor they have used, what elements in the hardware design they have taken, everything is volatile actually. So we spend a lot of time in doing this interworking to ensure that the system is deployed in the right sense actually. Okay, now let's see that how the architecture that will look like in the 5G actually. So if you talk about like a macro cell sub 6 gigahertz, they're all into the coverage area in dealing with its own capacity of the wireless transmissions. So why I call own capacity of the wireless transmission is that because if you see the propagation or the cell size or the cell radius we talk about in a thumb rule format. So we know that higher the frequency, obviously due to its own channel characteristic of the RF, cell sizes doesn't go beyond a certain range actually. Okay, so then it comes to the fact that if I want to do a larger coverage, I need to have larger cells. I need to have some cells up to 6 gigahertz. That's the bandwidth we are talking about, because in 5G, 4G we have taken to, I think it's 3.5, but in 5G we are talking about more than 3 gigahertz and up to 6 gigahertz. So every of this RF depends on the size of my deployment actually. How big is my cell I want to bring forward actually. Okay, so it means that if you have a higher frequency, your size of the cell reduces. If you have a lower frequency, obviously your cell radius you get benefited. But there is a caveat is there that how your multipaths or the propagations are actually in that area of this zone actually. If you have like a New York type of deployment, obviously your cells are too small actually. Even if you do a sub 6 gigahertz, we think of the cell radius will be some bit of larger. How large? How we quantify? It may land up in 500 meters, less than 500 meters also. Okay, because of the dense deployment, dense reflection zones that get created between the New York. If you have gone to New York, you'll see that how dense the buildings are actually. Dense in the sense both in height and both in close to each other actually. So it affects your wireless coverage. So obviously the planning, the network planning of the operator, they have to think forward that how I cater to, or what changes that I need to bring. Is your algorithm good enough to handle this complex deployment of this nature actually? So this is what will be seen actually as we roll out. Actually, we are not stopping the LTE coverage, and though in some places we stopped 3G coverage, we didn't stop the 2G coverage. It has its own benefit. So now question is that if I talk about the previous, I kept it open, but if you see LTE will be there for years to come. 5G will pick it up, and different flavors of the 5G deployment will come up with respect to the sub 6 millimeter wave and all this stuff. Pretty much it will move forward as we see year to year of the deployment. Now let's analyze now that if I have a base station now, okay, like how you split your functionality. See, base station, we normally say, oh, base station is there. It will do my transmission reception of in the wireless format actually, that is fine. But if you try to dig a little bit to the next level now, and let's go to the next level and this is our focus of today. I've just marked it out, though the other core network elements, I don't want to explain due to paucity of time. But if you see a base station, remember, if you saw the stack, hopefully you have the stack, we'll see what else are necessary to bring up a base station. So we'll try to define what is called the radio bearer actually, okay? And how to control the radio bearer, how to admit the radio bearers into the system, how you do the mobility of the users in the base station that you control. The mobility also will controlled from your core network also, but this base station plays a crucial role from the handover point of view, because he is the person who detects at the right time that a user signal has getting degraded, and the right time to do it. So it all depends that there are certain protocol, there are certain algorithms in place actually to deal with this first bullet actually. Okay, now I didn't define till the radio bearer. We'll define it as we come actually, what that bearer means actually. Now, what is the second point it talks about? And this is another base crucial element. It talks about the downlink and uplink scheduler actually. Okay, so this is not a 3GPP work item. So it leaves to the innovation of the base station vendor to innovatively come up and complex and to handle all possible deployment characteristics. Remember the deployment characteristic of the coverage cells, metro cells, massive MIMO, everything has to be taken into account. So how much complex your scheduler logic is actually, and what is scheduling we'll talk about much detail as we progress. Then what we do is that the biggest thing is that we remember we are receiving the internet packets, IP packets, okay? But the IP packets, when it enters the base station, it has to be properly header compressed actually. It has to be encrypted. It has to be integrity protected. If it is a controlled packet, it has to be integrity protected. So all those things is to be handled by this base station, and each protocol layer will, when you start dissecting, you will see that how each of this bullet fans out actually, that which protocol layer does what piece of the job of this top level statement I'm making actually. Okay. So it able to take care of the user plane packets. It able to control the information from the AMF. Suppose the AMF wants the base station to do something, so it has to handle the signaling from the AMF itself. And a lot of signals we'll talk about in details with respect to the RAN concept actually, and it able to deal with the mobility and other stuff. So it's a broad level that 5-6 bullet. If I make, is the base station is up and running? The answer is no. See the complexity in the next slide onwards. So before we get into the complexity of the protocol, let us devise that how the base station architecture looks like actually. So if you think of the dotted portion, I kept it purposefully here. Like you have to have a hardware, you have to have an operating system, and you have to have your layer 1 software as defined by the standard. But if you say that, okay, if I make a protocol in the layer 1 defined in the rule book or the standard document, will it work? The answer is no. So you need to have certain algorithms for a layer 1 to do the layer 1 processing, because 3GPP doesn't get into the algorithm aspect of anything actually. It never gives the deadline only gives the guiding factor that how the performance of the layer 1, including the algorithm, will looks like actually. Now you should have the layer 2 and the layer 3 protocols. Remember, I'll talk about layer 3, layer 2, given the stack view. And plus you need to have the algo, and you need to have an application layer who governs everything. You should have the FCAPS, what we call as the ONM, operation and administration security elements software actually, that cut across all the elements of the logical blocks of the base station. So if you have this one, and then you need the RF, this is where the actual wireless starts happening at. Now I kept it little separate here because in 2 reasons actually, because I have to talk about the OpenRAN. So then how much I split this logical entity will see it. And purposefully, I didn't want it to go in the RF section of this presentation. So I kept this boundary of my things within the purview, though this element is still hardware, but I'll talk only about this part in this slide itself. So you can think of a base station. It has to have this full gamut view, and we are at this stage here. So we are what hardly 20% or 25% of the overall system of the base station complexity actually. Okay, I have just take out the hard RF.
Sorry to interrupt.
Yeah.
So I have a question. I mean, 3GPP just gives us the guidelines. Then what does it expect us to do? Like, forming the algos?
Yeah, algos is where your innovation has to be there actually, because they don't govern what this, they tell you what the algos needs to be, means of the functionality. But there is a question of what and how. How part, the 3GPP never tells you how to do it actually. So that is where it is left to the innovations to devise all these algos, actually layer 1 algo, layer 2, 3 algos.
Okay, and if we put something in the algo that is not defined in the 3GPP or it does not specifically states that, then it is fine.
No, 3GPP never says, it gives you the performance of this block. Okay, so what it expects to do actually means, see, remember, the broad element is that if your algo is not meeting your latency, so obviously your algo is not fit to be in the product. Suppose the algo is not functioning and gives you an block error rate or CRC failure, because CRC failure is was 3GPP entity. So if he is not able to curtail that part, then your algo has to be optimized actually, or has to be redesigned to meet the end criteria. What it defines is the way the functionality has to behave. Okay, suppose I tell you that the operator takes into account and say the block error rate of the layer 2 should be 10%. Now you devise an algo in the layer 1 and layer 2 in together, layer 2 algorithm, that doesn't meet your block error rate of 10%. So it means your algo design is not right actually. Maybe your approach has to be relooked. Okay, because if you start losing 10% of your blocks actually, so you are end up in 90% of your throughput. So suppose if I want to give a user 100 Mbps, and he is actually want 100 Mbps of your tariff plan, and you give him 90%, means 90 Mbps you're giving, will the user be happy? Tomorrow the 90% may go down below to 80% also. Okay, so you as a user, I'm buying a plan, but I'm not getting the quality of experience. What he sees the experience, what the network guarantees is the quality of service. So both has to meet together actually. Okay, now if I tell the network algorithm who is giving me 20% cut in my throughput, and I'm giving a throughput to a user of 80 Mbps where he demands 100 Mbps, the user will not stay to that operator. He will first call up the customer center and say that I'm not getting throughput. They'll do something, but the fundamental problem, if it is algo, then it is whatever you do, it will not fit to the bill of this product actually. Okay, now 3GPP never tells you that whether 80% or 20%. It only gives you that, okay, I give you the bare criteria of sustainability, but he cannot define the user. As a user, I have paid something that 3GPP is not concerned with actually. So what I am concerned and try to buy a service from my operator, that is between me and the operator. That 3GPP is agnostic to it. Okay, so that's the reason that comes is that operator questions a vendor saying that, show me that how you, first of all, you have to meet the 3GPP minimum criteria that you have met. But operator has its own criteria that, okay, I cannot want my user to lose 10% of his throughput actually. Okay, theoretically, that is what your design may be, but I can only give you a leeway of 2% losing throughput. So it means that if I sell a plan of 100 Mbps to a user, I am okay with 98 Mbps, but not 90 Mbps. Okay, now these are the constraints that the operator puts to the vendor, that how good is your algos are. Okay, you are compliant with all the messaging stuff and invoking the right time, that is fine. But since 3GPP never talks to the algo, they are more concerned about to the vendor that show me your algo. How you're designed that meets me my demand of my network. Okay, that's the way it spans out actually. Okay, is that answers you?
Yes, got it. Thank you so much.
Okay, so let's move that. This is the base architecture. Now let's me start getting into one by one. Little quickly, I move from the physical layer point of view so that I jump to the layer 2 quickly. So let me start picking up the first part is that there is an RF spectrum that the operator has to buy. So there are certain terms that is very needed, though we call as a physical layer, but the entity is the MAC or the scheduler that will ultimately land up actually. So that physical layer term, he's bothered actually. He's very interested to know the scheduler. Why? Because when the operator buys a spectrum from the government actually, so the spectrum get auctioned from the band actually. Okay, so we'll talk about the band next. But two terms is important here. One is called the channel bandwidth. Actually, that is the overall bandwidth that the 3GPP defines actually. Okay, that okay 100 meg. Remember that term called 100 megahertz. So here is that 100 megahertz term actually. That channel bandwidth equal to 100 megahertz. But actually, what happens? There is some guard band that happens, but my actual transmission bandwidth is little less than 100 megahertz. Okay. So just to ensure that why we keep this guard band, because of the hardware RF entities like power amplifier, it has its own characteristics. So if you say that if my channel bandwidth is 100 megahertz, within that 100 megahertz, the power amplifier has to work actually. Okay. That's the reason his operatable bandwidth is called transmission bandwidth actually. Okay. And this transmission bandwidth under the purview of 100 megahertz channel bandwidth, this defines your physical resource block in the OFDM format actually. Okay. Because now if you say I cut my channel bandwidth, say 50 megahertz, so obviously your number of transmission bandwidth also get reduced. So, okay. So this is very two important terms that we try to see that, or the layer 2 is asking for from the layer 1, that, okay, how I am configured, how the physical layer has been, or the RF has been configured, what channel bandwidth, because moment you tell his channel bandwidth number, immediately I'll know my total transmission bandwidth number. And this is where your total physical resource block, or within this, the physical resource element get defined actually from the 3GPP point of view. They're all standard mechanisms are there. So this is the number he is more concerned. And see, let's see that how the spectrum get auctioned actually. So this is one of the spectrum table actually that is governed from the standard. So it is governed called band to be auctioned. It talks about the mode of the operation, like whether this band is meant for FDD, frequency division duplex, or time division duplex of transmission. It talks about if it is any of the mode, what is the minimum and maximum frequency that is allowed for that band actually. Okay. And if it is a duplex, full duplex, then you have the uplink downlink. If it is a TDD type of thing, you will think that this part is vacant actually, because you know TDD does the switching, because at a time in which at certain point of time the base station will transmit and the mobile will receive, and in a certain point of time the mobile will transmit and the base station will, and they happen in more linear synchronous manner actually. Okay. Then they talk about, I jumped this sub carrier, if you see in the kilohertz, and it will talk about the channel bandwidth actually here. So it spans from 5, 10, 15, and up to 100. Okay. Now this is what if you buy one carrier or a band or a specific, when the operator gives you, when the government gives a band and a spectrum. So the ideally 3GPP wants that the operator should be getting this to experience 5G. Okay, it means that let's take an example here. It's a band name called N1 band, 21 megahertz. What is the minimum is 21 and 2170 actually. Okay, it's a FDD band of the spectrum. The area of transmission is defined, and it can only support 5, 10, 15 at 15 kilohertz HCS. Remember the physical I talked about. The 5G has a flexible subcarrier spacing. So if you configure your network as 15 kilohertz subcarrier spacing, you get this option. If you configure at 30 kilohertz, I will talk about the numerology very shortly, but then you can get this of the channel bandwidth of operations. Okay. So this is the way the spectrum get auction. Now, question is, do an operator get full 2100 band? It all depends on government to government, geography to geography. If they want to split this bandwidth into two such operators and all the stuff, this is up to the operator and negotiated with the government how they are to planning this, the deployment of this bandwidth. But if suppose you get into the TDD N78 part of it, now you can see N78, this is what India has auction, and majority of the auction in the TDD has happened actually. Now see the total bandwidth has been allocated. It's a 500. If you see the minimum here, 3300 to 3800. If you take the difference here, it comes 500 megahertz. Now in India, each operator has been given 100 megahertz of the bandwidth. Okay, this band supports 500 megahertz, but they have given in 3 chunks, 5 in 100, 100, 100 actually. Okay, and that's the way they have auctioned it out actually. Now, operator now can configure in any form factor. If you see, he can configure that this 30 kilohertz subcarrier spacing, he can, then he has this channel bandwidth of operation. Now then it is up to him, means up to the operator how he wants to play with actually, because that's where government, neither 3GPP will put their head, because till you maintained your channel bandwidth and which band from this lower part, suppose you have given 100 megahertz from 3300. So your operation of your spectrum is 3300 to 3400 if it is 100 megahertz given to you from government to the operator. So within that 100 megahertz starting from your lowest ARFC or lowest marker, if you stay within that, well and good. So depending on that, you plan your network and your frequency planning, reuse your base station, what you want to give, that is up to you. Which numerology you want to operate, nobody will come and try to ask you the questions on that. So this is the way the spectrum get auctioned. But why I brought this topic is that because the layer 2 is more interested to know not this number, because he doesn't want to get into the RF part of it, but what he wants to know, what's the channel bandwidth I have been configured with. Okay, because this depends in his transmission bandwidth and his total number of subcarriers he wants to use it for his scheduling opportunities. So similarly, in the
I have one doubt here.
Hello, can you be louder?
Yeah. Actually, I just wanted to know one thing. As you have explained the things regarding band from network side. So is it applicable on UV also, or any UV camp on any band, or there is some limitation? With the RF perspective.
Okay, 2 questions I'll take. See, normally, if you see UV, obviously it is a small form factor wireless device actually. Now in that small form factors, suppose if you tell UV, and by the way, one thing I didn't tell you that this is not N1, N2, N40. You can see this list is a huge list actually. I just given a snapshot view of the spectrum, how it looks like. Now, as a UV vendor, if in that small form factor, I cannot scan this multiple bandwidth because there is a hardware limitation. Why? Because each band has its, as a bandpass filter, it's a hardware element that concern and cost of the phone. Suppose the UV says that I am compliant with all the bands of the world. There are some 80, 90 rows are there. It is humongous task for from the reality perspective, that I cannot have a wide bandwidth filter. I cannot support, because my processor cannot process so many bands due to the physical limitation, due to the hardware limitation. UV supports subset of this whole band actually. So he takes up the majority bands, and when we buy a phone, we have to look forward this part, that whether it's a global N1 band support. Suppose I buy the phone from India, and I have to see the spec of that phone to see that which band it is supporting to. So that if I know that, okay, I'm going to say US geography, that suppose N2 band, I'm going to China, that suppose N40 band, though India also supports N40. So I have to know that which area I want to roam actually. If I take this phone and switch on into my roaming partner in US or China or in Japan or Europe, I have to know that which band that geography is catering to, and the same band is being there in my phone or not. Actually, that is first part, because not all bands will be supported in the phone. Major bands are supported. The second part is the scanning actually. the band scanning is very proprietary algorithm from the device vendor actually. Okay, that is not governed by the 3GPP. Now, hypothetically, just imagine there are 72 rows here actually, or 80 rows in this band, and the phones support all 80 rows. You have gone to a geography that is, say, N79 geography, and the scanning of the band of the device starts on N1. So it has to scan all the bands N1, N2, N3, N4, N5 till it reaches N79. You can imagine how long you switch on your phone. You have to wait to see to get into N79 and then get a respective carriers or the RF SIMs to start doing my procedures. So it is not that efficient enough. So what the UE vendor normally does is that it manufactures phone based on the band, the majority of the band it picks up. Say imagine that US, China, Japan, Europe, these 4 top continents, whatever countries, wherever, whatever the bands they are supporting it, they have auction, they try to put it as part of their normal phones actually, and they leave out the rest of the bands as open actually. And in the way it has happened in 4G also, in or any of the earlier technologies of 3GPP, that the majority of the bands are supported in, and we also follow the same bands what the other geography. Like for example, if you follow our auction, we have auction N78 in our country itself. So now N78 has now become a global band, a band actually. Most of the countries are supporting N78. So you'll see phones, the first phones will come with N78 band actually. Okay.
So
Yeah, okay, thank you.
So to continue this question, I have one question.
Yeah, please carry on.
So it's very difficult to scan in each and every band by phone. So what is the limitation to put which the band supports by the operator into the SIM itself?
See, SIMs are again, what is the content of a SIM? See, SIM stores your home PLMN actually, where you are trying to roam or from where you're bought the service. Now just imagine when say you're in India, operator X, he has its roaming partner across say multiple countries of the world. Just imagine multiple countries. Imagine a scenario, because remember, we have given a flexibility of so many bands. Each country has chosen one of his band transmission, N1, N2. Say country number 1, N1, country number 2, N2, country number 40, N40. Now it is in that small memory, you cannot tell that, okay, you are in this country, so let me put, because I have a roaming partner agreement with this country number 40 or country number 1. Okay, so it means that suppose you want to do it to your own home operator, Mr. Operator X, that you are going to country number N79, where he has configured N79. You have to tell your operator that please put your information of that band so that I'm going to N78. Theoretically, everything is possible, but just imagine your SIM is not a large memory device, neither your phone, because we buy phone from a shop that is not given by an operator in India, though that is different in other countries. But India, you pick a phone from any of the shop, you just buy a SIM. SIM is the low memory device that stores the necessary information, mainly with respect to your authentication, encryption, keys, and everything to authenticate in your home network and to the network where it will roam into, and your home PLMN and the forbidden list. That means that there are the list in which you are not forbidden to get into the network. That's called the forbidden list actually. So these are the few information that the small chip is getting storing. Beyond that, that information, by the way, takes your 80-90% of your memory. Now, top of that, if I start putting country-wise band, it can be done, not a problem. But you will get exhausted every time you go to the operator. And just imagine in India, 500 million subscribers. Out of that, at least say 20% goes to operator every day saying I'm going to that country, this country. It is an unnecessary burden for the operator to keep. And so they try to avoid it as much as possible. They tell us that, okay, whichever country you go, ensure that, or now we are also become little knowledgeable that I'm going to that country, I have this phone, let me see that whether it supports the band in that country or not. Okay, that, and more or less, people are trying to reuse. If you see major countries, or most of the countries are picking up the bands that are more or less getting used by most of the countries. It is not like one country, one band, another country, another band. It was coming into that, but later on they try to dissolve as much as possible to make it more harmonized. This list is very big list. It is humongous for an operator to provision and handle so many customers, so many bands in that small chip.
Thank
Okay.
you.
So likewise in the millimeter wave, again, these rows are 4 or 5 rows are there. I have just picked up one of the row just to give a glimpse that we have N257 band 28 gigahertz TDD operation. Now you can see the bandwidth, very large bandwidth. But remember, this is a millimeter wave communication. The subcarrier spacing is only 60 and 120 because that is what the standard defines. And that's the way you can get your channel bandwidth up to this number. And if you want to have multi-carrier transmission, you get a double of 400. That's the way you want to configure. That's the way the spectrum was been devised by the standard and taken into all my elements planning actually. Okay. So after the spectrum, let's move to the basic of it. I don't want to spend again more time here. These all things you are now seen it 100 times for the last so many years. But what happens is that typically the layer 1 characteristic based on though the layer 2 is not bothered unless only about this number actually is bothered. But other than that, the symbol duration, it changes accordingly. The cyclic prefix, the symbol per slot, subframe, all the stuff is been defined and this has been taken from the standard. There is nothing rocket science here. So I don't want to spend time. That's to give a glimpse at how the layer 1 behaves. Now, this is a little bit of time I want to spend here, not on the numbers like the waveforms I talked about, that in the downlink, we maintained in 5G the CPU FDM. In uplink, we had earlier the DFT spread. Now we added CPU FDM because of uplink throughput demand actually, because CPU FDM demands gives me high multi-layer transmission. But this DFT spread is used for the power limiter where the SNR is weak and all this stuff. We try to use CPU FDM. So this two things the scheduler wants to know. He doesn't want to get into the algorithm part of it. Why he wants to know is that with this, if he knows that the layer 1 has been configured uplink as a CPU FDM, he knows that the single user multi-layer transmission is enabled in the uplink. So I can try to schedule in such a way to extract more information from the uplink means of device to the base station. This is what he wants to know from this number, but nothing more than that. He doesn't want to get into other part. Now let's see that what other things he is more interested into actually. So he is more interested into is that, okay, what is my slot and my symbol duration? I jump to the second slide. It will be a little bit of more useful if you see. So typically, if you see in the 15 kilohertz, he wants to know that, okay, if my subcarrier spacing is 15 kilohertz, then immediately the scheduler or the layer 2 knows we are talking about the subframe of a size of a one slot, and 14 OFDM symbols are being packed into. And this is very important information for him, because when the scheduler is scheduling a packet for the users and multi-users in the multi-access system that we are talking about, he want to place the packet or the symbols or layer 2 from the transport or the packet point of view in symbols and in the frequency domain of the OFDM grid. So he wants to know that which subcarrier, moment if you say I've been configured with 15 kilohertz subcarrier, so he knows my subframe length is 1 millisecond and one slot of 14 symbols of OFDM is been packed into. If I configured with 30 kilohertz of my subcarrier spacing, then he knows that in a total subframe of 1 millisecond, I have 2 slots to operate on actually. So like that, if you keep on going down, so each of this brown color is nothing but 14 symbols have been packed. So in 1 millisecond, how many slots he has to deal with it? And this is most important for him because he is doing the scheduling at the slot level actually. Okay, so he has to know the slot width in time, and other complexity will come. And for URLCC, he's more bothered about to know that what is this mini slot scheduling level, where we are trying to do at symbol level, OFDM symbol level scheduling. Means out of that 2 symbols I will use to do my scheduling, out of that 4 symbols or 7 symbols. So pretty much he's getting into, initially he was more interested into the slot numbers. Actually, now he's URLCC, he's getting into the symbol level actually. Lowest granular level it has gone into actually. And this is very, very important aspect of it, because you can see the complexity of the scheduler that is moving actually. It has gone to he has caught up to the symbol level. And that is where symbol were typically was kind of a gamut of layer 1. But now you can think of, he's sitting at layer 2 and he is getting in the layer 1's gamut and telling layer 1 that please do this in this symbol, please do that in that symbol. So he's dictating. He was a dictator of doing the scheduler, but he's gone more into that lowest level because of the URLCC, because of the 5G use cases he has to deal with it actually. Okay, so this is the most important aspect of the scheduling part of it. Now, other part, this is happening in the time domain actually. Now, what happens? Remember, it's a OFDM actually. So you have a time and you have a frequency grid. The frequency grid is for every symbol actually. So he's bothered about that. If I configured with 15 kilohertz, I know my slot and how many symbols and what is my slot length actually in time. But what is my maximum RB length in my frequency, that he's bothered about, because this is what he thinks that this is my entity for doing my transmission bandwidth. That is that number of PRBs, the physical resource blocked, that he want to deal with, and how many subcarriers. Though in 4G and 5G, the number of physical, this is the minimum granularity that he is talking about. The physical layer works in this granularity, but the scheduler works in this granularity of it actually. So he is bothered about that, how many such subcarriers you are packing in physical layer in one of the physical resource block, and how many such resource block have been provisioned here actually. Part of my which numerology that I'm talking about. This mu is nothing but we call as a numerology that is associated with my subcarrier spacing actually. So these two informations are from the waveform that the scheduler is very much want to be aware of it actually. Okay, so this is the take of the slide, that the scheduler wants to know that, am I doing a symbol level scheduling for URLCC? Am I doing a slot level scheduling? What is my slot duration I'm talking about? And what is my frequency of my bandwidth that I'm talking about, the physical resource block I'm talking about? Okay, these are the information that he took it from this slide. Now what he's interested to know that typically the physical layer, it has been taken into what we call as the transport block, the logical block, transport, and the physical channels where the information has been carried over actually. Okay, so in 5G, what has happened is that we have some of the physical layer channels, what we define, does certain characteristic of it. Some with which we send control information, some we use for the data information, sending data in the downlink. These blue colors are for my downlink and similar blue colors for the uplink actually. So this is what the scheduler is must be aware of it. Why? Because there are certain physical channels that he controls the information what to be given at what time. For example, if I want to send a broadcast information that has its own periodicity, at the right time, the scheduler has to schedule the broadcast information, means broadcasted from the base station to the overall cell actually. So he has to know that what is my periodicity of my broadcast information and what is the information that will go. Now, information is not generated by the physical layer. Physical layer just behaves like a black box. Okay, he knows that this is I have to deal with my black box level of my channels. Somebody has to fill the information for me. And who is the somebody? Sometimes the MAC is somebody, layer 2, I'll not say MAC only. MAC is the last element, the layer 2. and something is coming from the layer 3. So there are certain things, the control informations that also comes from layer 2 and layer 3. There are the broadcast information comes from the layer 3, and there is obviously the downlink shared channel data actually. That is what the MAC does, the multiple access transmission comes from the scheduler, both in the uplink and how you get the information from the device, that is uplink. Okay, so these things is very, very important where he is bothered with actually. Okay, and he has been associated. And let me jump before I jump. And he's also been associated, not the knowledge, but we'll see how he's planning the DMRS for doing the demodulation of my informations actually, whether sometimes the control, sometimes my data informations, and how my sounding reference has been concerned, what I get it from sounding. This is a very complex piece of things that we'll deal with one by one. So let me just quickly go over to it. Like when I say a physical layer dealing with the control and the data, so this D is for the downlink, and this is what the shared and the control C means actually, and P is the physical. Now let's see that when I want to send the data information, so transfer block is nothing but a packet coming from the MAC. Okay, so it has to do the segmentation, it has to do the channel coding, it has to do the hybrid ARQ, it has to do the rate match, scrambling, modulation, layer mapping, and all that stuff. Now I talked about, he works as a black box. Now who gives this fundamental information actually from where it comes? So it means that it is coming from the layer 2. Okay, now how layer 2 gives, we'll talk about that one. So physical layer, if you see in the uplink also, uplink, when you have the uplink shared channel information, means you are pulling the information from the device. You are concerned about to de-CRC it, to de-channel code, because UE has done his job. You have to do the reverse part of the job actually. Now, how does the UE knows that I have to do the modulation of this nature? Who tells me? Again, it's a scheduler in the base station tells the UE through control informations that please do this job, please do that job. And how the control information happens is that we do with this physical downlink control information, channel informations, where the scheduler gives the relevant information to the physical layer and tell physical layer that please notify these to the UE for downlink, and please notify this to UE so that he can send uplink information to me. So now you can imagine that the sum of this, the brain of the data transmission, the brain, heart, is in the layer 2 aspect of it, and especially the guy called scheduler actually. So he is the entity who is a multifaceted guy who is controlling a lot of this information. There are certain information that is inherent to physical layer that he will not put his head, but he will, for example, he will not tell that please do this LDPC. That is his physical layer job. That he will tell, please don't tell me, I know how to do it, my job. But what I need from you is that tell me that for this user, what type of modulation and what type of code rate that I have to use for that user for this transfer block you have given to me actually. Okay, so this is where the scheduler is one of the important heart, that he controls the physical layer, how he wants to do it. Okay, so now the question is that if your control guy is weak, and one of the question was asked, that algo is weak enough not to know how things has to be controlled, then it's not a physical layer problem. Okay, because physical layer is being told what to be done actually. So we have to see, unless until there is a software mistake in doing that job in physical layer, as a software engineer, if you think that we have not done it correctly, that is a one-time activity. But beyond that, it is not the physical layer problem. Physical layer says that most of the information comes from my layer 2. So please talk to layer 2 if you get into the problem. Okay. Now, what happens to the uplink? There are a lot of this control information. This MAC wants to know from the device. So the device uses a lot of this PUCCH, what we call uplink control channels. And at different formats that standard has defined. Okay, so please use this format, that format at the right time. So this is what the standard has defined, and the device picks up and sends those control information. Now, what control information it is? It wants to send to the base station. Like control information means whatever the channel state the device has measured in the downlink, he wants to report back to the scheduler to help him doing the scheduling. Okay, he wants to tell, okay, what is my buffer? I'll talk about a lot of this information that the device wants to communicate to the base station. This is what the physical layer of the device will try to do it. Okay, now this control information augments to do the scheduling. What called augment? Okay, it means that if you don't tell, can you do the scheduling? Yes, definitely I can do the scheduling without getting the feedback. But will it be optimized? The answer is no. So what you get augments your decision. But if you try to do with your own, you may land up in sometimes making wrong decisions. And one wrong decision, two wrong decision impacts what? Your throughput. Okay, so you cannot take a chance of keep on making wrong decisions. So you need some kind of feedback from the device. And device will be configured to keep sending you that information. You can tell device, don't send me, to again configuration. Okay, so this is the way the physical layer works actually. So the physical layer I also is work on the primary synchronization, secondary synchronization. I skip this topic because it's a more physical layer part of it. But what, if you see this picture is talking about, is that where is my location of my broadcast information? Okay, now the very interesting part of it. So if you see that there is a center frequency that has been defined. Okay, remember that band. So if you take a band, there is a center frequency, and your OFDM carrier can be put in up the center and down the center frequency. Actually, that's the way your PRB location, and people try to have it. But in 5G, you can see that somewhere in odd location, this is in the time, this x-axis in the time and y-axis is in your frequency grid, the time and in the frequency. You can see a very odd place I have kept my resource block. Okay, the broadcast information that has been there. And this broadcast has been placed on, that's very odd location. Now, this is what the flexibility we want to show, that it's not necessary that we have to keep in the start of the location. Any point in this grid, we can place our this broadcast information to it. Now, why? Who decides? Not the physical layer. The decision happens much in bigger context in the layer 3. So the layer 3 guy decides at where I want to place this entities actually. Very interesting. Why layer 3 will decide where the layer 1's problem actually. Okay. So let me skip this slide because let me take another two informations that will augment my decision of the scheduler. Is called sounding reference. So sounding reference is where the EV sounds the whole bandwidth, and the base station obtains the channel state information. See, the base station obtains. Now, which entity of the base station is interested to know this information? Which entity? And that is not the layer 1. Layer 1 does his job to get extract, but it's a layer 2 guy, especially the scheduler, is entitled to use this channel state information to variety of do a lot of things. Okay. Similarly, this happens in the uplink. Uplink means the mobile sounds this bandwidth. If you think of this is my frequency domain and this is my time. So he can sounds in one symbol information. He can sounds two symbol. He can sounds 4 symbol informations. Okay. He also can multiplex. If you see the color code here, like the violet, the brown, yellow, reds, and all the stuff. So at a time, you can see the 4 users information are being sounded on that OFDM grid. Okay, now how it is in synchronized, like 4 users are specifically been going. If you just look into this violet, here in violet, then got repeated in violet, repeated in another violet zone. So this is where the layer 3 configures the device. So one of the biggest entity I'll talk about is called the radio resource planning actually. Like how we do this grid planning. Okay, this is a very important task of the base station, that how you play with the flexibility that 5G has given to you actually. See the flexibility, I can configure a user
if you just see the red and this one, for the red got repeated only few times in one symbol, I can configure the same user red with two symbol, and I can multiplex in different RB with another violet, with another yellow users. This is where the flexibility of the 5G starts coming into play actually. The next part is called downlink channel state information. So this is the entity where the same job, the mobile does it for me. It means the base station configures the CSIRS, the mobile does the measurement and reports the whole measurement back to us. And there is a slide I'll talk about. Just hold this point that how these things happen, because this is where every control happens with the base station. Because if I configure the UV with sounding reference and with the right configuration, the UV will sound and the base station will receive. Okay, how I do this planning is the important trick actually. Similarly, I configure the device that downlink side, I'll configure the very specific places on the reference signal of which will be measured by the UV and will be fed back to the base station for doing varieties of operation. And especially we use for the MIMO operation, we'll see how we use it actually, okay? This is an interesting stuff that we'll see how we play with this information actually. Okay, now let's get into the next level of the physical layer that the scheduler is worried about is called the TDD frame format actually. See, in the spectrum you have seen, when I say band N1, N78, they are called as TDD and FDD spectrums actually. Now, how the TDD patterns happen. So this is what the scheduler is very worried about, that tell me that how I dictate tell L1 that this is the frame level of my information will go. Okay, now how the frame format looks like? I've given a typical one information of the frame format looks like this. If you take D means one slot of D. Remember what I have written, one slot duration of 100 microsecond. This is numerology 1. If you just go to the numerology table, it points to 30 kilohertz of subcarrier spacing. Now in this spacing, this is the one slot. Within that 14 symbols has been packed actually. Okay, this D. So this is D, and it goes to 7D here. One special special slot we can configure as on which what we want to do, and then U to U. And then this frame get repeated after this. Now, what is the duration of this whole time? So this is 500, this is 500 micro 1 millisecond, and this whole thing is 5 milliseconds duration. So when we start thinking of any simulation or anything, we have to think that the base station is working in this frame format of 7D1S2U actually. Okay. Now mobile doesn't have to worry about it because mobile we configure, we tell them mobile. So mobile is only have to be capable enough to support TDD. Now frame format is what the operator decides. Okay, that the way he wants to do the transmission. Now this is one type of thing actually. Okay, so he can decide how many such Ds, how many such S, how many only one S, and how many such U's that he wants to place at what time. Now if you see this frame format, it is 3D, 1S, 2U, 4D. The total is 5 milliseconds again. Okay. Now it is the operator who decides the way my TDD frame format I want to put it in my base station. Now if you see in the TDD what will happen in the scheduler point of view, he will do the downlink scheduler in this D, downlink scheduling. He'll tell mobile that I'm sending a information in the downlink, please receive it, because the mobile at that time he is receiver. When the base station is in the D, mobile is in the U, means he is receiving it. Okay. So in the base station point of view, the mobile is in the downlink. I'll send down downlink information, mobile receives. Send downlink, mobile receives. Send downlink, mobile receive. This special slot, I have configured 6 downlink symbols. So in me there are 14 symbols were there. I'm taking 6 as a downlink symbol, 6 symbols as guard. Not Okay, I corrected, it's not 6, it is called 4 symbols as the guard. And then what he will do, he will take 4 uplink as symbols as my uplink transmission. So it means that from the base station context in this S, so I have taken up these approach to do my transmission actually. Okay, so D for downlink, full 14 symbol downlink, 14 downlink, 6 symbols for downlink. Then we have guard where the base station and the device changes his role actually. So from here onwards, the base station start receiving, and the device starts standing in this special slot U symbols. Then the whole U is taken by the device, where the base station becomes the receiver. And again, it follows the same. But in FDD, what happens? So we have in 2 frequencies. See, remember in FDD, we saw that there are 2 frequencies, one for uplink and one for downlink frequency. So when the base station takes the downlink frequency, he does the D transmission. And simultaneously, the uplink, the user uses the uplink frequency to do the uplink transmission. So D and U happens in every slot to slot. Okay, so this is what is the typical FDD that differs from the TDD. Okay, now this information is very, very important. The frame format that we have to tell to the scheduler that you have to work in this frame format, because if this frame format is not known, scheduler doesn't know what TDD frame format I have to use for. This is very important information for the scheduler.
Sir, how did we get 4 guard bands and 4 uplink?
No, these are this is 14 in this S. You have 14 symbols, right? This S I talked about is a slot, right? So there are 14 symbols are there. So 6 of the symbols.
OFDM symbols.
Yes, these are OFDM symbols. So each slot has 14 OFDM symbols. So in that special slot, we can configure 6 as a downlink, and we have to give a guard. Remember, guard is for switching from downlink to uplink actually. Okay. So then base station will switch, and then base station will start receiving it. So we have to give him time to do the switching actually. So this is where we configure the special slot we call with this format, 644 format actually. Okay. 6 downlink, 4 guard, 4 uplink.
Okay, got it.
Sir,
so that's
yeah, I have one question here. Like this frame format, TDD frame format, is this like pre-decided by the operator across all his base stations?
Yes.
Or is this something that can potentially be kind of runtime configurable or something?
No, this is like when you switch on your base station, all the base station has to follow this order. Now, why? Just see the example here. If, say, the operator configures one base station with D and another in this pattern, I'll call this 7D1S2U pattern. And the second base station nearby base station also configured with 3D1S2U pattern. So you can see that what happens here now, that this base station becomes an interferer to this U, because this base station is now want to receive not from the base station, but from the device. He's receiving his own device information, but the nearing base station is transmitting with D actually. So direct interference from D to U actually means base station interference. That is the reason in TDD, the network, when I draw that network, right, whole network elements, all the base station has to configure with the same frame format. Got it?
Yeah, I got it. But actually, isn't this severely limiting the operator also? Because a lot of times it is the use case which actually defines how many uplinks you want, how many downlinks you want. Like, for example, you really require a heavy uplink when compared to a downlink. Okay.
No, this number is changeable actually. You see a problem on this number.
No,
this-
but what according to what you are saying is this is like a predefined kind of a thing, right?
Yes,
So
it is predefined.
but
Yes.
actually, say for example, a particular use case actually requires a high U when compared to a D, right? So how will the operator be able to cater to such a use case request if he has already pre-configured his network for 7D, 1S, and 2U?
Yeah. So suppose this operator and this base station is now configured with 70. So what he thinks that in my cell coverage, my user, he knows his traffic pattern, by the way, because in a 4G, he knows that how we are using our phones. But he knows that in this cell, the demand of my users are very less in uplink. My demand of my cell is in the more in the downlink. So he has made downlink heavy in this in part of it. Now imagine in one of the cell, he thinks that, okay, I want to increase my U. Okay, but one of his neighbor base station is going in this format of 7D. So if he starts taking up U, he has to intelligently shift this pattern in such a way in time domain. Remember, they are all starting in time, not in same time. Say this is my time 0 of my base station. The another base station can start after 5 milliseconds, after say 3 milliseconds. That's the way we can define the patterns actually. So the base station to base station, they plan very minutely to see that if I make 2U, making 4U somewhere, it shouldn't interfere my neighbors who are going with 71S to U. But your question is that we don't change that pattern because we know the traffic pattern. Suppose this traffic pattern is not working. Why? How he know? Because he is getting a lot of information of unused packets from the device. So he thinks that 71S to U is not working out for me in this. He switch off this base station, reconfigures the base station, and again switch on, because runtime, this flexibility of frame format has a bigger implication. Why? You cannot tell mobile who is doing some measurement saying that from now onwards you have become like 3U, 1S, 7D. You cannot runtime configure a mobile, because remember, mobile did his cell search. Mobile has his uplink information processed at the right time based on what you have told earlier. Suddenly, if you change your frame format outright, he will get perplexed actually in the system actually. So runtime, no base station configure, runtime, no configure. There are other things get configured, but this base configuration, they see the traffic pattern at 12 a.m. in the morning, switch off, reconfigure, watch, reconfigure. That's the way they do it actually. It is a kind of semi-static we call, not automatic.
Oh, it's semi-static at least. Like
yes.
he still keeps the ability of being able to configure at given depending on his traffic pattern and things like that.
Right? Exactly. So it is semi-static, not static. Static means put it and forget. Semi-static means all these configures are changeable. But you cannot change, say you're running a traffic at say 11 a.m. now. You cannot switch on and suddenly my phone will go off. You got it, because I lose, remember, some of the D will be my broadcast information. Correct. Where the mobile is been configured to latch on. Suddenly I change a lesser number of Ds and one of the broadcasts is just sign out. So mobile will go and try to see it because he doesn't know the base station has changed his frame format. So he'll keep on doing the searching.
So this semi-static, when it is configured, then it is basically that all the base stations actually need to synchronize at the same time to switch on to that format.
Exactly.
Okay.
They're all TDDs, very synchronized pattern, because remember, okay, let me draw it for you here, then you'll understand that what this synchronization it affects in 2 seconds actually. So suppose you have a base station here, and this is what this 7D I'm writing, and this D, this D, this D. Now this is your start time, say. Though ideally I can start after 5 milliseconds too. So all have been started at time T0. Okay, but I can also start after 5 milliseconds also, because then I'll be same. I have been offsetted with some time also. Offset of 5 milliseconds, because this whole thing is 5 milliseconds. Now just imagine the scenario where this is T0, this is T0. Okay, now they are all two base stations started. Everybody's are having this 71S, no problem. Like 71S to you. And this person is also 71S to you. Now suppose you this by any means, then there is a GPS here because they are all synchronized to the GPS. Now suppose there is a hardware problem that happened where this base station somehow starting with an offset. That is not 5 millisecond offset. So this is the one delta offset you have added. Though his pattern is 70, but he is now shifted in like this in this format now. So there is a shift. So this shift will start affecting in some symbol where interference can start happening each other. And if the shift is large, you may land up where D is of 1 is being shifted and large 2 when he is doing his U. So this is highly avoidable situation. You have to avoid this because you cannot have any drift in anywhere of in your system. This very, very synchronized way you have to work on. And that's the reason we try to synchronize with GPS so that everybody is taking the clocks independently and we are all synchronized. We can start with an offset because not all base station, you know that today we are in Bangalore in one area. Tomorrow, another place, another 5G base station will come up. We cannot guarantee T0 in every way. So we have to offset and start it out. But we have to ensure that the time in which we have offsetted, the exact time is maintained actually. Else, any drift in time will lead to any of this interference at any point, either in the slot level or the symbol level. You got it because this symbol is also 4 downlink.
Yeah, I got this point. Basically, what I was kind of coming to was actually, like, for example, if you consider a use case as a robotic surgery or something where the uplink traffic seems to be very heavy when compared to a downlink. I just wanted to get in this thing as to how exactly the operator will actually provision for such high uplink rates when compared to the downlink aspects to some of those particular use cases.
So
because,
there are where we have all D patterns.
Yeah.
We have pattern called all UU patterns. We have pattern with some Ds and some S, some U's.
So depending on that, so
yes.
basically on semi-static scheduling basis, he can actually change this over.
No,
That's,
scheduler, see, suppose I switch on my base station at 10 a.m. Okay, so depending on my pattern, where I am patterning it out and ensuring there is no kind of interference like this scenario, D and U colliding. Okay, all this stuff, I start my base station here. Now I watch my traffic and then I see that suddenly one robotic surgery traffic is coming up every time here. So, and at this point of time, there is no point of having my 71S to U. Okay, then I can switch off my base station here, do my time of my robotic and switch on my base station here. So this is called semi-static. Okay, it means that I have to switch off everything, configure my scheduler, configure my layer 1, then switch on. This is called semi-static actually.
And that this has to happen across is what you're saying also, right? It has to happen across all.
See, if across has to be there, and also just to ensure that if I want to go in this extreme pattern of U's and D's, so you have to ensure that, okay, I know that the base station of neighboring, they are seeing each other with D and U, then it's a full interference. Okay, this has to be, this operator tries to see very, very efficiently. Okay, but in radio, you cannot guarantee that wave will cut here because wherever the multipath wave, it's very difficult. That's the reason we try to configure, keep it static as much as possible till we try to change the pattern at some point of time. Means we try to, if that base station needs all U, then we keep it all U. Most of the base station surrounding to it, and somewhere we try to overlap with these so that U's and D's are in totally in orthogonal manner actually. So that is a deep network planning. They will be doing it now. Robotic surgery where most use, or there are formats that the 3GPP demands. We are not into the scale of the deployment at this point of time because of this U and D planning actually. That's the reason we are trying to play with the scheduler now as much as possible. And that is the reason we start to invent all this URLCC so that we maintain this interference Interference is not 3GPP's problem. He has given you flexibility. It is your network planning issue that they will tell.
Okay, so
Okay.
I wouldn't want to spoil the flow or anything, but is there something like slicing or something that comes in as a help here in such kind of cases, or?
See, slicing, these are concepts that is not known to the physical layer.
Okay.
Okay, physical layer, when we say physical layer, what he is knows with whether I'm TDD, FDD, which spectrum, that's it. Okay, now imagine this is the time I have written in the time domain. What happens to the frequency here? That I have never written. Okay, because the Y grid is my frequency. Now slice is a concept in the frequency, but in the time, they work independently, because what packet I slice it here, ultimately I'm interested that that packet going into which symbol, because that is what the physical layer is more bothered about, both in time and frequency. But he doesn't know that something is sliced. He is not fully aware of it, because that is a logical level that we have to deal with it. And that logical level is dealt by the scheduler abstraction. So where physical layer is kept as agnostic as possible, actually. Is that okay?
Yeah, thanks. Yeah.
Okay, so let's
Thank
go
you.
to the next part called.
So one more, just a small query. Like each base station has a TDD pattern, like
Every
which
base
is
station
in.
has a TDD pattern, but the pattern to be in this example I've made, the pattern should be same for all the base stations. Okay.
Yeah, fine.
Okay, all the base stations should emit with the same pattern. Now the question is that if that base station, say this base station, is having some uplink heavy, where it is not meeting your U, within that U2 slot U, he is not able to position, then we have to change his pattern. But if you change this pattern, it has to be ensured that when U is for this base station, say this base station we have changed to all U, it shouldn't interfere with some guy who is in the 71 to U. Okay, that is what we call as the network planning of the TDD frame. Okay, so this is very, very important for him to ensure that the radio waves are not coming at very large and interfering at when he is in D.
Okay.
Got it?
Yes, I wanted to ask, like the UV also must know of the TDD pattern.
No, he doesn't know.
Okay,
He
so
need not know.
The base station is expecting D, like the downlink, like it's expecting the UV to be a downlink, but the UV wants an uplink. So at that time, what happens?
See, how the UV works is little different. Okay, that's the reason it's called cell search. So suppose I'll just write it down and put as SSB. So there is an SSB transmission happening. This is my SSB dots. Think of. Okay. Now this is what the broadcast information, the PSS, cell search, and SSS information is going. Along with that, we have the physical broadcast channel information. These are the three information being spread. Now, UV can switch on his mobile at any time. Suppose he is the power on here. So when he is powered on, UV is in the receiver mode. Okay, so he doesn't see he sees some garbage values here. He doesn't need, he got garbage. And he tried to find out, suppose he find his cell. By the way, there are two aspects of it. So here the PSS is coming now. So he tried to synchronize with the frame and the slot level, isn't it? Because what happens to the primary synchronization and secondary synchronization? One gives you the frame and one gives the slot synchronization. Now this is done with the downlink information, and he's still in the receiver. He's still receiving because he may not have got the full, he may got his frame boundary, but didn't got his slot boundary. Okay. Now he gets into he got some information. Now at this point of the scanning, he might have got his PSS and SS decoded properly. Okay, now he able to read his broadcast information. Now he knows that this broadcast information that, okay, now I'm able to sync with the base station. Okay. So he is now sync with the base station. Got it? Now with this base station synchronization, so now what is happening? Now, if you remember in his TDD format, suppose one of the Ds in, say, this is your 5 millisecond Ds. And so this is your 5 millisecond D. One of the slot of the D was carrying your SSB. Okay. So now you have synchronized to this level actually. Now, the frame format is now based on this reference now. Because based on his SSB, he knows, that is from the standard, he knows when to send the RACH uplink. Why? Because we send informations based on certain protocol that if you are ready to decode this broadcast information, and there are certain other informations that are linked to it, where he tries to hunt for the first uplink slot based on when he got his downlink. So this is what called the RACH and the synchronization signals uplink downlink synchronization. So based on SSB, he calculates when I can send the RACH part of it. Now RACH has to be sent in one of these U actually. And this is where we plan when the D of this SSB will be there. You're getting what I'm saying here. You cannot arbitrarily send any D as SSB. So because you have to take this D for which he knows when to calculate send his RACH. This is where the RACH will go. This is what is the downlink to uplink synchronization is been done. Not this D may be some other data is going, some other data. This D may be some data plus SSB is being sent. Now mobile first hunts as a receiver to this D for this getting this information. So based on this, he gets his uplink slot calculated, and this is where the RACH will be sent. Now once the RACH goes, then the base station takes over him, because then only he knows that he's into my network first. You got it. So you don't have to tell anything. It happens just automatically based on the SSB and the RACH. Moment he sends the RACH, the base station is first then aware of it that I got a RACH. And then he takes over. Takes over means he will send the remaining part of the message to, he'll schedule message to at somewhere here at next D. So then this is where the synchronization, the slot, and with his downlink, he's tried to see the frame format, and we tell that this is the 70 part of it. So this is where first this is open. It's an open part of it, that the base station keep on transmitting, the mobile keeps on listening. Got it? Then comes the other aspect of the thing, because we don't physically configure the mobile. Okay, that this mobile, this frame format, it is not done. So there is a procedure through which he'll come to know, and that procedure takes over by the base station. And then only we keep on going that based on that procedure, because this is what is called as the frame and slot and the frame format synchronization. And that procedure will keep on happening till mobile and base, because moment you are out of that, if the device is out of that procedure, that U and D are all become redundant. That's the reason I was telling. Suddenly, if I switch off in all D format, the mobile is based on this procedure. He knows when D and U's are coming. And suddenly in the base station, if I switch off, he is expecting something at D where he becomes a receiver. But if I wait suddenly as U in automatic manner, then mobile get confused. He doesn't know what to do. So then what he have to do easily is that please switch off your mobile, switch on, because then he'll again repurpose himself. Okay.
Yeah.
So just to add one question here, does it the same architecture and same workflow is same with the multi-user MIMO also, or like if we have a multi-user, can we have a multiple frame formats?
No, see, multi-user is a scheduling concept. Okay, it is nothing related to the user and other stuff. So user doesn't know that how the scheduler is manipulating the resource block to me and other my neighbor. He doesn't know. So he goes as an individual. He thinks that, okay, base station is treating me as an independent entity. These all things have been planned at the base station. We'll show that, like, so user is totally agnostic. He only knows that, okay, I have been configured to receive in this PRB with this modulation and this number of layers, MIMO layers. That's it. Now, I don't know whether my neighbor UE is also transmitting the same RB by the base station. So in the network, each user behaves individual format actually. He doesn't know what I have to do. So user to user, there is no relationship. He doesn't know what information is going. That whole thing is controlled by the scheduler itself. He is the master. So all the tricks is played by the scheduler. User is totally agnostic. You got it?
Okay, so in
Just,
that, yeah, so in that case, one user, like just taken like that same example of remote operation. So that remote operation is kind of one user and other user is normal users, but BTS or base station knows what is the user about that. So in that case, slot format got changed for these two users.
See, there is a spec standard talks about that, the dynamic slot format indicator they call. Okay, this is one of the feature of the 5G. So actually we can tell mobile that please change your slot format. Means how you are trying to place your symbols with D and U. This is dynamic. But this has to be managed by the scheduler. So it means that this user, and this is the scheduler. So I can have SF1 for one user, I can have slot format 2 for another user. But the managing the interference and all this stuff is done by this guy. Because this is not the frame, remember the slot format, I'm changing it. In which I want to equate with how many symbols playing with that kind of information. This is dynamic. The slot format that I have placed 644, this I can change for that user to user. But I have to manage the interference between the users and between the entities actually. That is not been governed. You got what I'm trying to say. I can manage that. I can say for some users 6, 4 and 0. I can say 0, 4, 4 for another user. I can configure say 0 to 12. Now this is, I can manage. But what 3GPP will never tell you that if there is an interference that is coming out. Now I'm managing, remember that I'm making uplink heavy here. And in some case, you should ensure that when this guy is uplink transmitted, there should be no interference in the uplink who is doing in some, I'm doing some, he's downlink for another guy. This is not the job of this. This is the job of the scheduler, not by the 3GPP. So this intense management is very complex logic where I'm changing dynamically the slot formats actually. This is permitted by 5G. But the frame I'm talking about, when the larger base station, when I say that this is my 7D1S2U or 3D1S, this is the base station parameter. This is semi-static. I have to switch off, switch on, switch off, switch on. This I cannot manage. I can manage the S slots. This I can manage by the scheduler. But the scheduler cannot manage the frame actually, because frame is a concept of the RF, concept of the hardware, concept of the layer 1, with which the layer 2 knows and he governs this packet. So that has to be done in a semi-static manner. But the S, I have a liberty to do whatever I want. And the interference has to be managed by the scheduler, not by anybody. Is that clear?
Got it. Yeah, got it.
Okay, now comes to the fact with my bandwidth part actually. Now, this is my 100 megahertz carrier bandwidth, if you see here. So this bandwidth I configure, and this is where we, in 4G, we used to call network slicing actually. So here we say similar concept, but we say the bandwidth part actually. It means that the big bandwidth can be broken down into smaller bandwidth, and I can place my relevant users, relevant services tuned with that bandwidth part actually. And I can configure what is my size of that bandwidth. If you see n size, I can configure where my size will be actually. Okay. Now this is also semi-static, means that we have to tell to the user during the switch on time that base station is been configured with, say, 2 bandwidth part, 3 bandwidth part, 4 bandwidth part. And we have to tell the user also that this is what the base station bandwidth part has been configured. So it has a start RB and number of RBs, start RB, number of RBs. And we have the liberty to tell, and mobile, if he capable of measuring the full 100 megahertz, and he can able to switch now saying that, okay, I know that, okay, I have been configured with 3 bandwidth parts. Now where the data will be given, because now mobile is open to see all the bandwidth part. Now it is the job of the scheduler to tell mobile that your data is coming in bandwidth part number 1 in this slot, in bandwidth number 2 in X slot, in bandwidth number 3 in Y slots. So it is the scheduler who decides that I have been configured the mobile in this way. Now, based on my traffic pattern service, I can place the user's service. Say the user has a VoIP or say a voice over NR and one YouTube's high video streaming. So voice requires small RB. So I can place the users in my small bandwidth part for the voice. But his bigger YouTube streaming can go into some other bigger bandwidth. So that way, what I'm doing, I'm slicing my service into my actual hardware bandwidth part actually. And this is the biggest part of the 5G to play around with this bandwidth part accordingly actually. And this flexibility ensures a lot of things. The biggest things that will come if you see with respect to the battery saving. Okay, because the mobile is not told to, though his hardware is 100 megahertz, but I can configure with him just 10 megahertz, 20 megahertz bandwidth part. He can observe very small bandwidth initially. And then when he has a big data, I can pull him out from that small bandwidth part to a larger bandwidth part accordingly. So that is the job of the scheduler, he does it. Okay, so this is a big concept. The second big concept is the cell splitting actually.
Sir, one thing I just wanted to know about the bandwidth part. Actually, as per the 3GPP specification, it has mentioned that for one UV, there will be 4 bandwidth part, and at a time, only one will be active.
Yes.
Correct. So in that case, as you said that we are doing slicing based on the carrier bandwidth. So at a time, only one bandwidth part is active. So how it will be sliced for different services?
Okay, let's give an example. Good question. So let's see that I have 2 bandwidth part. Okay, now this bandwidth part I want to his voice or NR go, and this part I want to play some high speed EMBB service. Okay. Now, what is the quality of service of this? This say every 40 millisecond I have to send 1 packet actually. And here in this part, let's say that every 5 millisecond, I have to send 1 packet of VMBB. Okay. Now imagine how the scheduler will work. So if this is your time scale. So in time, every 5 millisecond, I am sending 1 of the packet. This is EMBB, so I'm using bandwidth part 2, telling him that you get your packet, you tune to this bandwidth part to get your packet. So like this, it is going up to 8 times comes here, right? So this is your 40 millisecond from here. So 40 millisecond, I will tell that this is where the voice packet has to go, because else every 40 millisecond, I have to send a voice packet. So here BWP1 will go. Okay, now here what happened, BWP2 is off. So I sacrifice only 1 slot of information for BWP1. Got it? So now what I have to do that next from here, another 5 millisecond has passed. So here regularly I can send BWP2, another 5 millisecond BWP2. Got it? So this way the
Yes.
BWP is there. Now what happens is that suppose if you see here, I didn't raise my size of the packet. What size I want to send? I omitted here this number. So what I'll do, suppose size is X bytes I'm sending. So here what I will do, I'll send X plus delta bytes. Whatever I lost it here, I can compensate in subsequent actually. So overall, if you see, and if I take a snapshot view here, that let me see how my throughput is being seen. So on an average, I am able to, suppose I have to send say 10 or 16x packets. At this case, if I am able to deliver 16x for that EMBB, then my throughput is guaranteed, isn't it? There is a little bit glitch happened here. So that I will to make up with sending extra bytes here. But at this point of time, I am able to send all the packets for the EMBB. So my throughput is guaranteed. And at this point of time, my voice is also sent. So voice is also guaranteed. So your bearer or your application EMBB is guaranteed I got, and voice over NR is also guaranteed. When at this point of view, there is a glitch, but this is hardly what 500 microsecond glitch happened. This is nothing from user perception. This is the advantage we take actually. You got what I'm writing, right? So how we plan our scheduling, this is the scheduling logic. That how you plan your scheduler to work so that you use your time, you use your person's quality of experience as its notion and start playing with the bandwidth, playing with the packet size, playing with the modulation, playing with anything. This is the variability and this is the complex scheduler.
It means, sir, it means that at a time we can access 4 services only. As per the 3GPP, we have only 4 bandwidth part allocated to the one UA at a time.
See the trick that has gone actually. The trick here is that you're taking a view at certain point of time where, see, it is not at a time. What is measured is the quality of service. Now, what is quality of service? Quality of service means that based on whatever the service you have started, you are guaranteeing a throughput. You are deriving a block error rate. Got it? So if I am able to guarantee this throughput, if I guarantee my latency, that packets are not queued and latency for that quality of service, for that service is met, then how I schedule my logic is very internal matter. For me, it is seamless till I get my packets on my phone. But as a network bothers about the quality of service. Means he doesn't want to see the latency of the service is growing. Means the packets are queued, but no output is happening. This is a dangerous scenario because packets are getting queued. So it means the latency is increasing. So this is I don't want. So if I'm able to flush my packet at the regular point of time, then my latency is guaranteed. They are going out and not staying in my network queue buffer more what it demands. It means that my throughput, whatever the service of 100 Mbps, suppose he bought a service. So every say 100 milliseconds, if operator takes a dump of his value, 100 millisecond, you cannot distinguish in our eye itself. But the network is working and giving you 100 millisecond of guarantee that every 100 millisecond, I ensure that your 100 Mbps is, this is my observation time, but I take a snapshot view that I give you a guarantee of your 100 Mbps throughput, what you bought. That is well enough. So this is what you have to see. If you see that you are not getting into too much buffering and too much blur actually, then my quality of service is guaranteed. How I schedule my logic, how many packet I'm sending at a time, 2 times, that is my thing. Whom I'm sending, that is where the jugglery is happening in the scheduler. Is that clear? But scheduler is taking user to user. He takes one user, we'll talk about that. User. And then he's taking that snapshot view of that user, and then he's trying to correct for that user. so that the overall quality of service is not disturbed. That is also he's trying to see. But also he's also trying to see that I'm not focusing at only one user, because then I become very biased actually. I'm not fair. So that also view he has to take, that he cannot be biased. He has to be fair. A lot of criteria goes into making the scheduler work. So that, see, the complexity happens in the base station is that when the capacity increases, and we are talking about base station who has thousands of users in his plate to serve. When the capacity increases, your hardware is limited. You are not putting in a supercomputer 1 base station. You have a limited hardware. You have to deal with your anomalies of your RF. You have to deal with the anomalies of the wireless channel. Still, you have to guarantee a quality of service. It is a multi-facet optimization problem. But too many maths spoils the whole stuff. So we have to balance how to heuristic, how to optimization theory. Both comes into play when we start designing a scheduler in that complex. Small schedulers, fine. But large schedulers, you'll see how complex the chapter. So first complexity is bandwidth part, like putting the right user with his right service enabling at the right bandwidth part. There are more complex you'll see as I slide down. Okay. The other part of my planning is my cell splitting. Okay. So here cell splitting means that typically, if you see from the operator, we normally say three sectors, say every sector is 1 degree apart. I put antenna to do my radiation of my coverage. This is where the way my coverage is being designed. Now, suppose what happens to the users here? These are my intersector who are potentially my sufferer user. So they start splitting the cells actually. This is with the more putting. So it means that 3 sectors has become now 6 sector cells actually. So this is also the scheduler is worried about, because now initially I was dealing 3 sectors. So each of 100 meg here, 100 meg. Now you added 3 more sectors. Now tell me what is the bandwidth of each of these sectors are actually. So it means that 6 sector scheduling I have to do. Now think of the complexity. 3 sectors, so many users. To get all my users in the cell, if in this geography, not a single user are left out in this, the cell sector boundaries, I have told scheduler to work on 6 sectors now actually. So the loop complexity increases. And you don't know what bandwidth the operator has configured this sectors actually. Whether 100, 50, 20, you don't know. Okay. Now whether FDD or TDD, that also I don't know. So now imagine 3 sectors, TDD, he may have 3 FDD sectors also. So now he has to do simultaneous transmission of the TDD, FDD users. All is the next level of complexity. Okay. Another big complexity will start coming with the beamforming. And this is the most crucial part for the presentation that will come, is called the beamforming actually. Now beamforming in 4G days, we have seen the beamforming. So it's good that we have seen the 4G performance of the beamformers actually. And that is the reason what happened when the 5G beamforming came actually. So we know that beamformers are some kind of energy concentrated view actually. Now, whether you do with a digital level or you do with a analog level, digital, or with a hybrid. So each has its own efficacy when to do it, at what level to do it actually. Okay. Now, is it necessary that can I stay only with digital? We cannot give a clear answer that everything we can say to be done at the digital beamformer, but I don't have to do with analog actually. This is also cannot be guaranteed. For certain channel condition, you have to enable analog. So then why you need digital? Because digital gives the flexibility to deal with UV to UV. Okay, so I can distinguish UV1 and UV2's beamformers actually. But analog is wide actually, means all EVs. So this is a problem. The problem is, if I treat all the users same, I can do it and form the beam and concentrate. Suppose I have a base station and all my users are here very much co-located, then I can make a single analog beam and keep my SNR high here actually. That is one way of doing it. So I can usually do it analog beamformers actually. So, or if I want to treat user separately, then I have to get into the transmission in the digital domain and play with the digital weights that I want to give it to user to user. Now, if I need both these two flavors, then I have to go with a hybrid actually. There's no other option. So this is where that comes to the fact that we have to know that in a multi-antenna system, if you have a transmitter receivers that is configured with actually, that is where the RF. Now you will see that RF concept been pulled into the scheduler level. So I have to adjust the phase, I have to adjust the amplitude accordingly and give us the perception that the energy is sharp or the energy is wide. Now this I'm doing it at my digital level, changing it or not using the analog phase shifters and all this stuff. I can play with that. It becomes hybrid if I use digital and analog. So this, how to do it and how and what is the mechanism that standard gives, then why you need algorithm? If everything is given by the standard, then where is my flexibility of my algorithm starts? So let me take this one as the first concept that let's, in this thing, we'll use the digital beamformers actually. Okay, now remember two concepts I talked about from the physical layer. One is called your SRS actually, and one is called the CSARS. So this is used for the uplink channel sounding, and this is used for your downlink channel sounding. Okay, so there is a concept called open loop and closed loop actually, MIMO. Okay, so what happens is that in the open loop, so suppose my scenario is like if I have my base station and I have my users and the base station is transmitting the CSIRS towards this EV. I can tell EV that please, whatever you measured, you please give me feed it back at a regular interval of time actually. So this is called the periodic measurement actually. And what measurement I expect from the EV for this, the channel state info reference signal in this configure in the downlink, that I want to know that what the rank the EV is perceiving it. Okay. Tell me the rank, means I want to do a multi-layer transmission to you, right? So what is you think is the best rank you are trying to perceive it out actually. So I need to know that one. So I get to know the feedback. And moment I start getting the feedback, I get into the closed loop MIMO actually. Okay, means I am dependent on user to give me something, and then I'll do something. So I'll tell user that tell me that which precoder means which beam that you are trying to experience most SNR, highest SNR actually. So this is very important, and tell me the channel quality. So this gives me to select my modulation and the code rate. So moment I tell that give me this three information, so I get into the closed loop MIMO aspect of it. But does it mean that I cannot do with an open loop? Yes, you definitely can do it. But how accurate it will be? So we are bothered about accuracy of this open loop. Means without getting any feedback from the user, you are deciding the rank of the system. You are deciding the right beamformer or the precoder of the system. You are deciding the downlink SNR of the system. How to do it actually? Okay, now sometimes you may be right, sometimes you may be wrong. Okay, now here is a trick that we typically try to use it. Suppose you are in TDD system and we use the reciprocity principle. Okay, then somewhat I can rely to come out with my independent view of this three information: the layer, the rank, the precoder, and my SNR in the downlink, but may not be accurate. Now, why it may not be accurate? Because how I cannot randomly pick up the numbers, right? It is not a random numbers problem that I pick up and choose actually. So it will be based on certain measurement. So using reciprocity, can I use the uplink sounding and decide the downlink informations? Yes, that is feasible. That we can do. But where we'll get hit here is in the SNR. Okay, why SNR? You can get hit because remember that when you have the base stations, the downlink SNR and the uplink SNRs are not equal because SNR means SINR actually. This I is a downlink interference that the mobile can be told to measure and he can give me a best SNR and so now the question is that when I use with SRS SNR, if I tell SRS, you give me the SNR, he can also give SINR, but that I becomes uplink interference. So my uplink interference and downlink interference are not the same characteristic. So if it is not same, and it is sometimes it is not same actually, practically it is not same, then my SNR from which I derive my modulation and code rate, that also will be different. So moment I get into difference, I get into the blur in the downlink because I use a wrong SNR to decide my downlink MCS. So this is a problem when we start doing the reciprocity. Not every time that we get a right information, what is needed. So then how to correct? Mechanisms are there in place to correct it out. But let's move forward with the pre-coders. Let's see that what happens, the MIMO, the MIMO basic characteristic is that I want to do a multi-layer. Rank means that it tell me that what is the number of layers that is to be transmitted to by the scheduler. Now, how we calculate rank, that is a linear algebra problem. I'll not get into it. This is not the physical layer part of it. But assuming that the mobile gives me the rank, I measure rank directly to my number of layers. So if the mobile says my rank is 4, I interpret that I can do 4-layer transmissions actually in the downlink. Okay, if the rank is 1, I ensure that mobile is expecting 1-layer transmission. So this is important. Okay, because the rank gives me the information that what the MIMO downlink transmission needs to be done actually. Okay. Now, keeping in mind that let's see what the standard gives it to us actually. Okay. When the standard tells you, see, if this is from the standard table, that it tells you that when a user reports me a CQI, suppose this is the 3 CQI table that we have to tell to the user pre-configured actually through my RRC. So we have to tell to the user, and user gives me say a CQI value of this one. So what it gives me that CQF5 is a number. By the way, I don't know the SNR. Okay. So the SNR is not known, question mark. But he only tells me that CQF5 means that I am expecting a QPSK modulation and I'm expecting a code rate of this much. And that will give me an efficiency, spectral efficiency of this much. So any value you take, this is the very important things you'll start getting. Okay. Now what happens is that suppose then the question is that CQI is a number. How I relate to a SNR actually. That is very important part. So that we do it using a link level simulation. So we try to find out a relationship between SNR and the CQI. So if and this is been done through a link level simulation where we excite our link level simulator with a pre-configured modulation in the coded and observe what is the blur, 10% blur, and see the SNR, and that SNR gives me my CQI number 1. That's the way we normally try to create. So it means that as an engineer, we have to get a SNR to CQI mapping actually. Because the moment you know SNR, you can do a lot of things. With CQI, just a number, integer number. I cannot relate other than from this spec defined table. So I need to know the SNR. And once I know the SNR, then I can use my wireless concept to do a lot of magic things called power control, link adaptation, a lot of other things I can do it. But provided I successfully able to convert my CQI to the SNR in a right manner. And this is not that easy to come up. So we have to come up with this one to get the CQI to SNR mapping actually. Okay, now suppose I know CQI, no SNR. Take that example. Now what happens to the downlink actually? This is the slide I was waiting for. Now if you see here that mobile is been configured with the resource element. So if you see here the CSI information where it has been positioned in the grid actually. So the standards tells you that at what symbol and what frequency a configuration of the port will be to be done actually. So whether it's a here example is the 2 symbol informations and that it has been frequency done with the in the 2 grid elements itself. Now what is now it can change into any ways. That's the standard defined way. The standard also can tell you like in this format also. Now in this example, if you see, if I configure the same element, this blue color is going to the mobile. Mobile does the channel estimation. It does the noise estimation. And what it does is not known to the base station is the SNR. And he does the channel decomposition and get me the rank, the channel quality from here, he'll map it up. He tells me the best beam that is suitable for me. And he tells me that what is my RSRP value in dBm that this I'm measuring for this resource element. And this is now fed back to the base station actually. And who is most interested is the scheduler. Now this is the physical layer process that the mobile does it actually in his part. Okay. Now if I don't take the feedback, if you go back to the original slide here, if I don't take the feedback from the CSIRS, then my option is that if it is a TDD, I will use reciprocity and try to use through SRS. And I'll do the same job, like calculate the rank, calculate the CQI, that is nothing but my SNR, and get the beamer actually, the precoder or my beamer. Okay. How accuracy, that is separate part, but I have option to do it using reciprocity. So this is what sometimes is needed, is that not every time open loop works actually. I also need to have some view of my closed loop. Now the question is that which EV I use open loop, which EV I use closed loop, who decide, and how adaptive is this decision? This is the statement. We'll see, we'll answer that point. But this is what the channel state information is the most greatest part of your MIMO. Okay, now let's see that what happens from the precoder point of view. Like there is a concept when we configure the channel state information in the reference signal point of view. This is taken from the standard that how my antenna elements in a logical level has been provisioned by the standard. Okay, this is not the physical antenna elements. We'll see another slide to it. So it tells you that if you want to have 8, 4, 32, whatever antenna ports that you want to configure, typically this, to do the precoder or the beam estimation, you have to configure in this format by the standard. That it tells you that if you have an 8 port, you can have the option of having N1, 2. This is the number of columns and number of rows. So it means that 4 ones means 4 columns you can configure and 1 row. This is that configuration 4-1. Or you can go in this panel configuration logically. Now remember that here comes the concept of the antenna that if you have a linear array or this is a rectangle array, so if it is a linear array, you get the horizontal beam width and you can play with the horizontal beam width. Vertical is stationed. Here, compared to this, your vertical beam width get affected. So it means that you are trying to go up the azimuth and elevation to simultaneously using this configuration, because there are two elements in the row. So you can try to decide kind of the elevation and what is the azimuth beams actually. This is the most important concept of the logical to antenna mapping actually. Now, this is not the physical antenna, by the way. So the standard gives you the notation saying that if you are trying to configure an antenna port actually, for which the mobile is expected to give you a rank, because remember CSIR's basic funda is rank, the PMI, and the CQI. This is the most important things. If you want to get with this configuration, then your antenna has to be done in this fashion actually, the way it has to be radiated. So your information of channel estimation has to come in this order actually. Now, but physically, it doesn't follow. I have taken an example here. Like if you take this concept of 8x2, this element. So it is expecting 8 such columns and 2 such vertical elements. And what it also tells me that I can create a Nyquist beam, and also I can create the DFT beams actually with this sampling factor, oversampling factors. Okay, now 8x2 configuration if I take, then in my hardware elements of my RF, I have to have one element called TRXC virtualization that maps with the actual physical antenna. Means that how many such panels I want to configure where I can send the CSIRS port number 1. And these are my cross elements. So this is plus 45 and this is minus 45. So how many elements I have configured here? This is up to your designer. That 3GPP never tells. It is up to the antenna designer, and we have to think of that how my panels are to be given and how this panel will map me using this concept to my logical level. So this is my logical antenna port. And this is the actual physical antenna transmission that happens, physical antenna. And this bridging is done by this concept called TRXC virtualization. And here you have a flexibility. You can have 4 cross elements. You can have 8, you can have 11, up to the antenna vendor, what he wants to think. Got it? So this is where we do the logical to physical antenna port mapping, and because ultimately the wave will be generated by this concept actually. This is where the design starts, that how you want to do your TRXQ virtualization, what way, how much beam width you require to set that to cover. A lot of things goes in that concept actually. So this is what, now imagine, we are still into the estimation phase, because we told mobile that your configuration, that the base station logically from the 3GPP point of view is this much, but actual antenna is this much, but mobile will estimate this and do his estimation. But why we do this then? Because we have to cover a sector actually, right? A 120-degree sector we have to coverage. So let's see that how the beam looks like actually. Okay, let me skip this one. So I'll come back to this number, just hold on. So see the beams, how it looks like. Let me go to this table first actually. So when we did the simulation, this is the feedbacks that the mobile gives me to me actually. I want to, these are my index feedback. When I talk about the pre-coder PMI, so the PMI as a value, he gives me 3 such feedbacks actually, from where I can calculate the beamer actually. And the beam looks like this. So suppose this is a digital beam, it looks like using this pre-coder weight actually. Okay, now see the gain here. So this has some beam value. all my physical antenna is excited, and digitally the beam looks like this. This is my board side directivity. Now, as my pre-coder value changes, if you see, the -4 has become -7, -11, -14. This way the things are moving. Okay, you can see the directivity is changing. Here the directivity is slightly changed. Here more change, more change. So you can see that this beam theoretically means what actually. Suppose a user is in this board side with user here, and a user is here and a user is here. So he'll report a PMI says 0. This guy, depending on the angle in which he has been placed, and this guy has placed, he can report me a PMI value of any number, say this number 8. And this guy can report a PMI value of say 23. Because each beam is what the user is estimating. And he thinks that this is the beam that with which I'm expecting highest SNR. And this information is very, very important for our multi-layer MIMO transmission actually. Because if you want to get a feedback mix, and now the question is how this feedback is reliable. Can you say that if I give this PMI 8, I will give highest SNR and block error rate as 0? The answer is question mark. May not, because ultimately when you are giving me the feedback and when I'm transmitting the beam, if there is a time lag, then obviously I cannot expect, because you might have shifted a little bit here and there. So you might have got closer to somebody, interference has started generating. So it doesn't mean that the beam, what I estimate, is immediately being used by the base station, because obviously I have to do scheduling. I have to manage thousands of users. Everybody is giving me feedback. When the feedback is old, when the feedback is new. This is what the concept of the scheduler channel aging based approach starts taking into account. But the concept is, from the beam point of view, digital beam former, if the whole 3GPP downlink codebook, that when we say a codebook based approach, so it means that you take the 3GPP's codebook, means 3GPP beam formers, and form the beam and do the transmission and check what is the blur, what is the throughput, and all the stuff. Okay, but you may not guarantee that you'll get everything actually. Then what do you do? So 3GP also told us that if you're not satisfied with my codebook, you can use your non-codebook method, what you want. So means you have your own codebook and you run and you deal with the mobile independently, with some signaling has to be taken and all this stuff. This has also been there. So in 3GPP pre-coder or the beamer, we can have the option to tell mobile that I can use the codebook method, I can use the non-codebook method actually. Got it? So non-codebook method means it's totally independent and base station decide, and you can have flurries of algorithms to design your codebook, how sharp, how fat, directivity, how many beams for each layers, best beam, interlayer interference, a lot of things you can control by yourself. Okay, and who does that control and all the stuff? So this guy takes the ownership of doing that management actually. It's a big things that we have put it back in the 5G. Now this is what I skipped it out. So normally what happens when I say the CSI PMI feedback, when I say pre-coder or the beam feedback actually, so the mobile sends me this kind of numbers to me actually. Okay. So based on my how many columns and how many rows that I want to have configured, so it gives me one of the numbers of these DFT weights actually, and from which I can calculate, and there is an equation there, this type of equation. So you can use, so if you see the metrics of the pre-coder digital, these mu values are already given in the standard. So you can put these values, you can get this W matrix values here, and you can finally get a pre-coder and which has a directivity actually in this. So when you see a lot of literature, the internet, all this kind of things, and if they follow with the channel-based measurement, then obviously they are following in this order, getting the feedback, or they're going with their own ways of generating the beams actually. Okay, now these are the feedbacks from which I'm expecting from the mobile, and this is where the protocol comes in handy. That I tell mobile that give me your I11, I12, I2 feedback values actually, so that I can put in one of the table, and this table is based on how many layers that the mobile has that is nothing but my rank information. This is the rank value. So based on the rank, I jump to that right table. This is the rank 2 table, and you can see the 2-layer part of it actually. If you see single, it is a single column. So I can jump to the right table, get the I11, I12, and I2 feedback, generate the precoder, and I know that, okay, I can use it for the downlink transmission and precode to a multi-layer transmission part of it. But what happens, the concept is like this precoder is that when you precode this matrix, and this is what my previous slide is talking about, that if I have a precoding matrix, if you just take that I have a single layer data that is used with a precoder, single layer precoder, you can see that how the layers are being weighted by some numbers. Each weight for each apply to one of the whole one layer data actually. So it means that if this data is how it is going out from using the precoders weight actually, so you can see that how the fractional weight is been applied to the layer to the single layer data, and vis-a-vis you can see with the 2-layer approach, if the rank is 2, I jump to the table, I have a 2-layer precoder columns. If you have seen it in that, I have boxed it out. This is the 2-layer data X0 and X1. So you can see that I multiply this X0 with W0 and X1 with the W32, this part. Okay, now you can see this is the value that will be gone. And if it is the way we decide the matrix part of it, it is a 32 cross value. If I've taken a 32 port instance and 2-layer data I'm trying to send. So on a 32 port logical antenna, using precoder, using the PMI, the layer data are put, What I mean to say is that this is a 32 port information. You got a 32 port cross 2. This is a 2-layer data. You can see that each port, how my layers data are been fractionally put. So this is what the precoder helps me to translate my layers into my logical antenna port. But finally, from that, using the TXRU, it will be transmitted to the physical antenna system actually. So this is a sequence in which we apply the precoders. We tell mobile that give me the feedback of your beams and all that stuff. Okay. So this is all about the complex transmission of multi-layer, or sometimes we call as single user MIMO actually. This sometimes we also call as a multi-layer transmission, but in 3GPP term we call as a single user MIMO transmission. Now we'll come to the multi-user transmission, but this is what the single user transmission happens actually.
Excuse me, actually it is about lunchtime.
Oh, okay. So let's, can we break?
Yes, we can break, and we can continue the session from 2 p.m. So
okay, fair enough.
So let's stop here then. And it was really an exciting session for me as well, because I am also in wireless domain and I had been stick around throughout this session. So I do expect that all our participants are also equally glued towards their screen. But sorry for the interruption. This is a lunch break. We will meet at 2 p.m.
Okay, so we'll meet at 2. From here, we'll start going to the next details actually.
Perfect.
Okay.
Any questions you want to take?
Sir, can we get the recording of this session also after finish?
That we will be deciding, and once it's decided, and we can provide the link. It is available on the YouTube of our Comet channel.
Okay. Thank you.
I had one question.
Yeah. Please tell.
Regarding this resource element. So one resource element, is it like the difference between one PRB and one resource element?
Okay, see, physical layer is concerned about the resource element actually, because 12 resource elements makes one physical resource block. Got it? So that's the relationship, number one. Number two is that the scheduler is bothered about the physical resource block actually, because that is his minimum granularity with which he does the quality of service measurement. Okay. But the physical layer on that 12 REs or resource element packed as a one physical resource block, he had to add some more information to it actually. Okay, now what information? So within that physical resource element, I have to put a DMRS resource element to it, because suppose in the downlink direction, 12 REs means doesn't mean that 12 REs being taken by the scheduler. Okay, so there are some REs the scheduler will fill up the data, say YouTube, Times of India, whatever. Some REs he'll leave blank, because in that RE physical layer will introduce his DMRS information into those resource element. Got it? So in some REs, the physical layer wants to introduce if it is a downlink, say CSI-RS information into it. So that also I cannot take. Got it? So likewise, then the way we normally calculate is like this. Suppose I have, say, some resource block, I convert it back to RE. What scheduler will do, he will multiply with number of 12, say 2 REs. 12 into 2, 24 REs he got it? So in this RE, he will try to take that based on the space and time. You remember the grid, if you remember, he will start negating out the DMRS REs. Okay, based on what is the DMRS configuration that I have done it. So I will take it out the DMRS. Suppose per element resource block, I have placed 2 DMRS. So 2 into 2, 4. So 12 minus 4 gone. So 8 resource element is the worth of information that he will transfer, or he wants to put it, or Mac knows it, or scheduler knows it. He will transfer it with that 8 into account, not 12, because that is the reason. Another slide you will see later, that how we do this dimensioning of the total elements in the system actually. That's a big dimensioning element we'll talk about very quickly, that we have to negate all the sounding reference signal, the DMRS into account, SSB into account, because SSB, we cannot send data on that, right? The PSS, SSS, we have to negate all those PRB or resource element, minus what is left out is nothing but this is the worth of resource element that with which the Mac or the scheduler will see for transmission or reception, vice versa.
Okay. Like one PRP had 14 OFDM symbols and 12 subcarriers.
Yes.
So how does this 12 RE fits into it?
Not
Like
12 RE. See,
yeah.
one is y-axis is your frequency, but I have to take my x-axis also. That is my time. So I have to also tell the scheduler that is this. So you just focus on one row first. Let's take one PRB. You can expand it out 12, 14 symbols. Exactly. Okay. Now it means that you can see that how many REs you are getting if you consider 14 symbols. Suppose I tell you to the scheduler that don't use 14 symbols, you have only configured with 10 symbols. That also I can do. So then what happens? Your total number of RE changes. Now what is the total number of RE now? Now frequency domain, if you take this example, I told 2 PRB. I didn't talk about how many symbols now. Let me take now. So now 12 minus 4, DMRS, you have took it out. So 8. Now then my next question is, how many symbols? Is it 8 into 10 symbols, or 8 into 14 symbols, or 8 into say 12 symbols? It is all on the pod view on the base station configuration. And we have to tell the mobile also, by the way, because it's not like I decided mobile will intelligently know. This is not known actually to him. So we have to tell him that for sending the PDACH information where you will get your data, you are being configured with how many symbols and how many bandwidth. Remember, if I put another complexity of the BWP, I have to tell him very clearly that BWP, this BWP, you have to work within that BWP. Your share of that RBS is within that BWP. So many one by one information we have to convey to him. Else the device is also as agnostic as base station physical layer. He doesn't know anything. Okay. So there are a lot of configurations that goes into the system to make the physical layer of the base station aware of it. Then we have to configure the mobile to be aware of it. The mobile, when he powers on, he knows some, but he doesn't know all. Okay, so we have to make him aware of all. That lot of this RRC signaling I'll talk about actually, that ensures that he knows all actually. What base station is not known to all also from the protocol point of view. So means protocol, timers, counters, this, that, lot of things we have to make him aware of it. As he is total as agnostic as the physical layers are.
Okay. Got it.
Got it? So
Yes, yes.
all are flexible in 5G. You can configure the way based on the use case, based on what you want to send, what you want to receive from the user. Everything is configurable actually.
Okay. So just last one, like if I understood it right or not. So like 12 resource elements, it's from the frequency domain.
Yes.
Okay.
And every symbol will have that RE, right? If you just extend that row.
Yeah, like one resource element would have that 14
one
symbols.
symbol. Okay, okay, let me, how will I share now? Okay, let me know you have to see my screen.
Yeah, I can see.
Okay. Let me find one. Okay, let me take it here. And okay, so this is the symbols I'm writing. 1, 2, 3, 4, 5, 6, like this going. And this is one grid. You got it? Another grid. Another grid. Now this. Now take this as your RB, PRB. Now in this, you have elements like 1 to 12. This portion. Now this is where in one symbol, right? What happened to this symbol? This also has this one, right? This also has this. So now if you extend, I was talking like this. Okay. Now you can now start a dimension saying that base station can tell this user that for you, I have given only this much. For another user, he can say, for you, I have given complete one. This is on the purview of the configuration the base station one can do anything. But whatever you do, you have to convey to you the way you want to do it. Is that clear?
Okay. Okay. Yes, yes. Yeah, this helped.
So when we try to see what I was talking about, say 1 PRB, RB is equal to 12 RDs. So I have to do some overhead calculation then. So I'm doing for the one symbol level actually. And then I'll multiply with whatever n symbols that I want to configure. N is max equal to 14. So here, this 12 RDs minus this overhead, this is, we have to calculate that what is the overhead. Now, what are my overheads are there? So I have to find out the DMRS is biggest overhead actually. Because what happens is that every RE, so if this is my resource element, I have to block the DMRS positions.
Right.
So I don't want, if I want in a non-overlapping manner actually, means this is for my data and this is for my reference signal. So then I have to in a non-overlapping manner actually. They are distinctly in the frequency domain, they are separate. So then I have to take this minus over it. This minus becomes important. Got it?
Yes, sir. Got it.
Okay.
And sir, like one question, like have you taken any more sessions on this? Like, because I have like quite a few doubts, and like after attending the session, like my concepts has not been this much clear. Like I got a clear visualization. So like any more future sessions you're planning to take or you have taken earlier, which I can refer to, or like how can I ask you my doubts?
Okay, we'll see how the doubt can be clarified again. Okay, the
You
sessions.
can, Anveshna, you can write to us also. We can reach out to the Saptarshi sir and we can get back to you if you want something like that.
Oh, okay. Sure, sure. Thank you.
So now can we have a break for the lunch?
Yeah, we'll make it at 2 actually.
Yes.
Okay.
Yes.
Okay. So we will be meeting. So participants, they can go, and I will keep the meeting link on meanwhile. But yes, the session will start at 2 p.m. now. Thank you. Yes, good to go, sir.
Okay, so welcome back actually. So let this participants also joining. But see, from now onwards, let's start focusing a little bit of the massive MIMO. I'll not go into the depth of it with the paucity of time, but I'll tell you why layer 2 is should be aware of the massive MIMO concept actually. Now, the first thing is that let us define what is this massive MIMO terminology means as the layer 2 point of view. See, what happens is in the system actually, when we say massive MIMO, it is simple textbook definition of the number of elements, actual elements that the system adaptive arrays has been provisioned with actually. Okay, so what I mean to say is that here I try to define an antenna array system, subsystems actually. So each of these cross poles. So each of these cross poles, we can have a huge size of this. Means it is not like here 4 here and 4 here. So it is very small part of it, but you can think of where the system of this nature can go up to say 8 cross 8 means 64 elements. Cross pole elements we can think of. It can go to 128, it can go up to 126. These are the elements that adaptive array antenna is been provisioned with actually. Okay, now question is that you have an antenna. So does it qualify that? Is it massive MIMO actually? Okay. No, a few more things we need to add it up to qualify as a massive MIMO point of view. So what happens? Okay, I need to draw now, like we have the layer 2 here and we have the layer 1. And then we start the RF actually. This is typically the way we get our textbook knowledge of the RF interworking with the layer 1. But when we say RF, if you divide this RF into bigger things actually, so the first things that the base station is worried about that how many transceiver chains that this RF we are talking about. Now, what is mean transceivers? Transceivers means the RF chain that has the PA and the LNA loop actually. So this is my transceiver chain that will look like actually. Now just imagine that I have defined such 32 or 64 transceiver chains actually. Okay, so it means that back of my antenna, we are powering it with 32 or 64 RF chains actually. So in the downlink, this RF chain will excite the PA, and in the uplink, that this transceiver will excite my LNA actually. So this is my chain of operation of my transceivers, and 32 chain is been devised actually, and by some means that is what I call as the TRXU virtualization. In my previous slide, I talked about, let me go back to this slide once more, that using this virtualization, my RF hardware get connected to my physical antenna systems actually. Okay, so that is a very proprietary design that the RF vendors or antenna vendors both will work actually. That how many such transceiver chains we are talking about to connect to my adaptive array. Now we made that connection. The transceiver chains are up and running actually. So that the first things I talked about, the question is that we are addressed about the transceiver chain connected to my adaptive array. So the answer can be say 32, 64. That is what the current systems are coming up actually. So now question is this each of the 10 chains that we talked about, that this is one chain, this is another chain, another chain. So what will be my power amplifier rating actually? Like what is this value that we are talking about actually? So are you talking about a rating of the power as a 5 watt, 10 watt, or what actually? This number is very important. Because just imagine that just connecting 32 times of the power amplifier rating, the RF becomes very complicated both from the designing point of view, the hardware characteristic with respect to maintaining his heat sink, thermal, everything quadruples based on the amount of the rating of the PA that we are trying to put forward actually. Now, all in all, let's assume that we have made hardware quite a reasonable amount of for my transmission. 32 such chain connected to my adaptive array. So ready to go as my massive MIMO system. So my base station is up with my system actually. Now, once you make this base station up with this adaptive array system, then comes back to the standard. Standard means, see what we are anticipating now to do with the mobile actually. So why we have put it? Because we wanted more multi-layer transmission actually. Okay. Now, is that not happening when you didn't have massive MIMO? The answer is yes, we're still having it. Then why we need more antenna elements actually? Because now the greatest application of the massive MIMO we want to put forward is we wanted to use the channel hardening property and enable the multi-user MIMO actually. So massive MIMO as a concept was there long back actually. There is nothing point of view that my invention of my PA ratings, number of RF chains to be connected, the amount of big antenna elements that to be connected to my transceiver chains, everything was there actually. So what in the cellular industry wanted to use the channel hardening property and start making my multi-user transmission actually. Now, why they are so behind this multi-user transmission is the one single element of thought actually. Now, what is that element of thought? That if you think that this is my grid, my ORDM grid actually, if I think of in direction. So the way the scheduler was planning his resources to get some spectral efficiency value is that, okay, I give this resource to one element, suppose this one to one user. I give this one to another user, say this is user number 1, this is user number 2, this is user number 3. Like this I was trying to give. So what basically is like by default, the allocation was orthogonal actually in the frequency domain. So there was no interference because this grid of the user 3 is totally orthogonal with the allocation with respect to user 2 in the frequency domain. And also with the user 1. So I can do any services in this one. They will not interfere. The user 1 will not start interfering with user 2. So based on that and how much of the throughput I got it, remember my bits per second per hertz. So I can calculate my throughput, overall cell level, and divide by my bandwidth and get my spectral efficiency defined. So that was the number that was coming out actually. Now remember, we have to reach to the magic numbers what ITU has started defining it. So if I go in this order, the way I can increase my throughput is to increase my multi-layer transmission. Okay, that we have done it, like using the pre-coder in my previous section. We can go say from 1 layer to say 2 layer to 4 layer. And if mobile supports, we can go up to 8 layers per mobile. And that is also is very UE capability, hardware dependent UE that is still not there in the market. So we have a UE that is coming up to 4 layers. So if you get into 4 layers, suppose this grid, I give it to 4 layer for EV1, another grid of user for 4 layer user 2, that way I can get my efficient defined. But still the operator is not satisfied because they wanted to get the last mile output from this, the bandwidth, what they have actually procured. Then they thought that using the channel hardening property, can I use the multi-user transmission? And what is that multi-user transmission? Let us see in the next slide actually. So when I say multi-user transmission, let us focus on back to the grid actually. So this is my grid of OFDM. This is in my time and this is my frequency domain grid. Now, if in this grid, I wanted to do and get away my frequency domain orthogonality of my scheduler and start saying that like this user grid, I want to share with user 1, user 2, and with user up to n users. I can do it. Then what is happening, this part of the grid is shared by this so many set of users. This set of users are getting defined actually, or group of users. So they are actually sharing a part of that bandwidth. Okay. Now provided, now the greatest challenge is that, remember now we are breaking the orthogonality condition of the allocation, frequency allocation of the users. So we have to ensure, or who will ensure, the scheduler has to ensure that this user and this users or the group of users using the same PRV grid does not create inter-user interference. Inter-user interference. It is bound to create. Okay, but how I protect? So now, if you think of in that scenario now, so if you see previously in the SUMIMO system, suppose I have two users, user 1 and user 2, sharing the orthogonal grid. But here, if you see, I'm doubling the number of users sharing the same grid here, doubling, tripling, 4 times, 8 times, whatever. It's up to the amount that we want to pack it out. So more users you pack on the same resource utilization. So the more throughput you are getting. So what is benefiting is the cell throughput. We'll define next as what is cell throughput. So the cell throughput increases. So my spectral efficiency also increases into that order. But what penalty we are paying into account is the inter-user interference. So how much we want to pack the users. And if my beams, now I bring this concept of the beams, if they are not taking care of this inter-user interference properly, then one user's energy of transmission will fall into other user and vice versa. And they mix up, create inter-user interference. Finally, rather than seeing my spectral efficiency improvement due to the signal leakage, I start seeing the drop in my throughput. My cell throughput start dropping. So I don't get any spectral efficiency benefit. So now to utilize that fact that if I want to increase my spectral efficiency, still I want to go with a massive MIMO, channel hardening properties and multi-user transmission. What is the pre-coding or the beams and how to calculate actually? Okay. So this is the biggest challenge that happens as the design of the 5G schedulers. Moment the 5G scheduler starts working in the massive MIMO context actually, and we want to use the multi-user transmission, how you effectively pair users actually means this is what we call as a user pairing concept actually. So the pairing of the users is very complicated where we need to understand now, okay, you want to pair the users, but what the literature talks about using the pairing, there are a lot of materials in the literatures that talks about how to do the user pairing aspect of it. But even you do that theoretical part of it, you take the best in class of the algorithms that will enable for your user pairing logic. But still in the real world scenario, we cannot pair or we cannot get the total number of transmission layers that we intend to get actually, what intend to configure, intend to get it actually. Why? Because this inter-user interference plays a havoc role in bringing down my throughput actually, and that brings to my spectral efficiency. Now let's give an example what I'm talking about actually. Now hypothetically, if you see this arrow, what I'm mentioning it, just imagine that this is one beam actually. Okay. And I want to enable a single layer transmission for this user actually. I have another beam I have defined. I have another beam. So 3 beams to ensure that my users are orthogonal to each other. And that's the way my leakage is reduced. So if I, in a slot, if I put these 3 users, then I get up to say 3-layer transmissions for the multi-user. Same resource block they're using it. Now I can keep on making more and more like this actually. Now what happens in the real world scenario? Suppose you have a building here. You have a scatterer of some reflectors here. So they are all reflecting the waves here and there. Because in RF, it is not that you can control and say that directly whatever antenna you can do up to a certain extent. But where is your scatterers are? You don't have any control to your scatterers. So if you don't have a control of the scatterers, when I say a beam, whatever the far field measurement of these beams look like after the scattering happens, it may come to this side and this beam can go to this side. It means that there is an overlap in the signal actually. And there is a leak of the signal from, though we are saying that highly directivity, after scattering, the signal can go to here, user 2 signal can go to user 1 and user 1 signal can scatter come to user 2. And that's create your user interference. Now this is known fact actually. Now is that way that if I want to decrease my scatterer, and practically no, because your scatterer will be there and where your users locations are, the algorithm starts hunting it out that who are my right users actually. So this is the biggest that the simulation starts happening in the real world, that ideally how many users to be paired actually, and who are my users, who are my magic users, who ensures that the beams are orthogonal. There is no leakage from one beam to another beam. They are orthogonal and I reduce my inter-user interference. And that way I get my spectral efficiency benefit actually. Who are those users? What are my criteria of those users to selecting that one? So this is the biggest part of the logic starts, that what is your effective, however effective you design the logics are theoretically, practically it becomes very fuzzy actually. It's not that easy that we get the right users in a dense environment scenario with a lot of these clutters are already in place actually. So then you have to overcome with algo actually. You have to keep on thinking your constraints, filter it out, best users, how many layers that we want to consider for each of those users, what is their SNR to be considered, lot of things that comes into the play just to ensure I'm doing a research on this user pairing logic actually. So we start with the base literature, but things proceed to the level that to hunt for my best user to do my user pairing logic. So it is like hunting the best set to get my spectral efficiency. But there are more things actually, like after you hunt the users also, it doesn't mean that you have got the best things. Why? Just check these connections, what we have written here. So this is nothing but your RF getting connected to your adaptive array system actually. Now, what is the beam? We talked about the beam directivity just time back with respect to the SU MIMO. So each of the beam has its own direction. Okay, one direction you are trying to create actually. Now, what is a direction means? It means that there is a phase of that beam actually. Okay, and there is an amplitude and there is a phase. Simple. The beams are as simple as definitions are actually. Now, this phase we are talking about, where we are applying this phase of this, we are applying the phase in layer 1, suppose. Now, what happens once the symbols get generated actually? It has to be transmitted over the cable. There will be a radio. The radio unit has its own anomalies, say the path, PCB. They can create another phase addition. So what will happen to this phi digitally? Means if I want ideally to phi to be transmitted here at the antenna port here, if I want that transmission to happen ideally, but there are hundreds of non-ideal scenarios that it has to cross. Even a simple cable can add a phase to it, and whatever the fine beam phase we are talking about can get associated with another phase that can come any anomaly during this whole transmission path. Now, if you didn't calibrate it your whole system properly, then this phase is unknown that your simulation will never catch. Because simulation is a MATLAB. So it will take your idealistic scenario, whatever best. But if your actual hardwares that are there is keep on adding this phase, now what will happen a phase to it? It means that the beam is rotated at some direction. Now, which direction it will rotate, we'll never able to think of, because we are predicting the beam, right? So if I use the method that I talked about, like if I use the SRS sounding uplink and do the TDD reciprocity and finding the downlink beam, now where all the rotation is happening due to my hardware anomalies, this is unknown. So we think from the MATLAB, the simulation that the direction is like this, but even a slightest rotation can create an interference. That is unknowingly things will add up in my system. So that means my hardware is not calibrated actually. And this is the biggest problem of the massive MIMO performance actually, because more finer beam we are talking about. Remember, finer means your beam width of your beam. If this is the beam, your 3 dB beam width we are talking about. So this beam width is more finer it becomes. So any small change of using this anomalies in your hardware path will create a rotation, and we don't know where the direction, and ultimately it creates a signal leakage. And that starts interfering actually, unknowingly actually. So we think we are supposed to get after a lot of simulation, a lot of things, but practically when we jump into the testing, we find out nothing is achievable. So this is the complexity of bringing, though the theory looks very great that I'll bring up the multi-user transmission using massive MIMO elements and channel hardening, everything. But the section to realize this is still undergoing more and more for perfection. It is not that massive MIMO systems are not there in the field, that are already there in the field actually. But the efficacy of that algorithms, including how we have done our calibration well, ensures the overall performance of the multi-user MIMO actually. Okay. So this is what the biggest complexity or biggest challenge when we start getting the massive MIMO based system, and top of that where we are trying to bring forward the multi-user transmission actually. Now there is no scheduler here play. So scheduler is agnostic of what is happening in the hardware. So scheduler takes the best effort to find out the beam, find out the user, the precoders and all this stuff. But scheduler cannot control the hardware calibration. This has to be done a priori before the scheduler makes his decision actually. Okay. So this is about the massive MIMO and the multi-layer MIMO. Now let's put the puzzle together actually. So in this puzzle, I talked about that there is a component called protocol. There is a component of the algorithms in place. And what 3GPP gives us is this protocol stack to adhere to that. If it is a base station and you are doing a control plane means signaling, I want to do. So the stack will do its own functionality based on this mechanism in the EV side. And what is required in the base station side, the equivalent peer-to-peer has to decide upon actually. And I talked about non-access startup has its peer entity in the AMF. This is a part of the core network actually. Okay. Now this is the signaling plane. Similarly, in the control plane, we have this layer 2. When you say layer 2, this is my layer 2 box. And this is the control plane layer 2. And this is my layer 3 aspect. And this is the layer 3 that we also call layer 3, but it is The context is with respect to the core network, not from the base station point of view. Since we are in the base station, I'll try to omit this NAS at this point. This is my layer 2 and this is my layer 1 actually. Now this is the overall part. Now let's get a glimpse that if you see all the complexities that we have discussed, more are there. So how we put the puzzle in doing the functionality break actually, because if you don't divide your functionality into across the layers, they all jumble up. It is not like a one monolithic software doing every part of the story actually. So what the standard has evolved in so many years actually, where they have broken the functionality into layer by layer. And here we don't follow the typical OSI layer because it's a 3-layer communication we type to do it. But sometimes we say the physical layer, sometimes we say the data link layer, network layer. All these things is those fancy things what we define in the IETF is not here. But similar things are there actually, because still we have a MAC layer who does what the OSI's MAC layer was supposed to do, augmented by RN, RLC and PDCP to it actually. Okay, now we'll see that that how each one of help us actually doing my transmission actually. So if you think of a packet actually, now the packet, if you think just imagine this is the top entry of my base station. Okay, so this is my user plane because you remember the SDAP, PDCP, RLC, MAC and PHY. We'll restrict at this point no PHY here. But if you see an IP packet, a typical TCP or UDP IP or TCP packet is waiting, that is came from the internet, came to the base station. So we define the quality of service at the right flow. We'll define what this SDAP will do. So we do the flow handling and we create the pipe. We'll show you the pipe, how the pipe looks like and create the flows here. And let this pipe goes back to the PDCP layer, who does some bit of the header compression, who does the integrity and the encryption of the packet. Remember, 3GPP has its own encryption and integrity protection. Integrity done on the signaling packet and encryption done on the data packet. So whatever he uses some security policy based on what algorithms he wants to do it. Now he passes the packet and each things will show you that how the header get added. The packet moves on to the RLC layer actually. Okay, now here we can see that that packet is the first time we'll see the segmentation of the packet is happening actually. Now why we do the segmentation? Because we know what is the capability of in the RF with respect to that, the spectrum RF, I'll say, with respect to subcarrier spacing and all that stuff. So I need to segment the packet accordingly and send that segmented packet one by one to the demand, to the scheduler part of it actually. And the scheduler will multiplex the packets for each users and pass it on to the physical layer. And then if it is get into HARC, he'll handle the HARC actually. Okay, so this is a typical, the flow in which the packet is moving. If you see the life cycle of the packet, it is moving from top to the down actually in the downlink direction, if you think of. So, and in the uplink direction, the mobile will do it and you have to do the reverse what the mobile does it. Okay, the similar flow is already there in the mobile, like the way the downlink happens. But you have when we receive the packet or the base station receives the packet, it has to just do the reverse what the mobile has studied, because in the mobile, it is not multiplex or multiple mobile, it is like single mobile packet. But when we get, remember the uplink OFDM grid. So based on the grid, the scheduler knows that from this grid to this grid, the user one packet is lying. So I'll take it out and give it to MAC. MAC will give it to RLC, PDCP SDAP, and then it goes out to the internet from to the core network through the internet. Now this is the packet life cycle. That typically what we call actually. And here is this guy sitting in the scheduler. It looks simple. Then we'll define what is other complexity of this guy. So this is a typical life cycle of the packet. Now let's see that what the MAC layer does actually on that packet actually. Now we are just imagine we are moving down actually. Okay, so we are here at this stage. We are the MAC layer. So what the MAC layer does is that he asks RLC that what is your logical channels of your packet definition, and I will map that logical to the transport channel, relevant transport channel, and how many such transport channel definition, sir. I will go to the next slide itself. So he will do some multiplexing in the downlink of the packet of the max SDUs. He will put the scheduling informations that is required to be given to the UV through the physical layer of. And if you get into the HARC, he'll put his head into HARC and it will do some prioritization of the packet and all this stuff. Now, this is very simplistic prioritization. Nowhere in the real one, you'll see the complexity later on actually. Now, MAC, if you think of, it looks simple from this 5 bullets, which the MAC is done. No, the MAC is not done actually. So the MAC handles, if you remember, I was talking about the RACH actually. So the complete RACH procedure, MAC handles at that, has its own capacity itself. MAC handles the downlink data transfer, uplink, receiving the packet. It handles the request that is coming from the device when the device has the data to send. Means we'll come to that, but just imagine at this point of it, that is called the scheduling request, where the device tells the network that I have a packet or I have an information to send. So please give me grant to uplift my information to you actually. So this is all handled at the MAC level actually. Then it handles, MAC handles the discontinuous reception actually. It's a big activity that he has to plan for it. Now it has to handle the semi-persistent scheduling. Now what is this word called semi-persistent? It means that it is a fixed scheduling slot, especially used for voice over NR traffic actually. So at fixed slot, it has to schedule the voice over NR packet actually. So I think I have given that example a few slides back, that how we schedule the BWP and voice over NR AMBP traffic. It has to do by the MAC itself. It has to be involved in doing the paging. Paging means I have to wake up my user actually. And it has to involve in getting this broadcast information. Remember, I was talking about the broadcast information, so it has to handle to it. So you can imagine that this is what is the demand coming from both from the packet and some protocol demands. So this entity has to be aware of this part, means it has to take care of the signaling part, and it has to, because signaling is also a packet for him, and it has to handle the data packet also. Data means YouTube, Times of India, uplink, downlink, whatever reason means. So much of complexity it has to handle actually. Now let's see that the logical to physical mapping actually, what the standard talks about. I'll not start getting a glimpse of it now. So this is what the transport channels that is been defined from the standard point of view. So here on the MAC stays here. So he's interested, if it is a paging, he want to pay to the page transport channel and call it appropriately the physical layers to it, because every of this transport is mapped with some physical channels actually. So you can think of MAC does a bit of grouping. Why? Because he wants to do some prioritization actually, because if it is a single pipe, suppose you didn't have this information with the MAC, it becomes a single pipe. Then MAC doesn't know that which one to send what at what point actually, which one to stagger, which one to go front, which one to come later next. This is the MAC's job, he has to do it actually. So what the standard has gives the flexibility that whatever the logical packets that are coming from the upper layer, means who is the upper layer of MAC? RLC. So send it accordingly and map it out to the relevant transport channel, so that the layer one, when he receives this transport channel, by default layer one knows that what to be done, including the information you want him to do it actually, means what code rate, what modulation, how many layers, what extra information you send it out and give it to the layer one. So this is where what we call as a logical channel to the transport channel mapping actually. And this is done by the MAC layer. And based on that, we play around with a lot of things actually, like which one to send next, which one to send later, block him, send, all these things that the MAC is trying to do here actually, okay? The next part of the MAC it handles, it is called the real-time trigger actually. It means that he doesn't expect the upper layer. Remember, there is a signaling part I talked about. So which is much above. At the RRC level, we expect things to be done and then things works actually. But if the Mac wants to do some real-time signaling to activate, deactivate a lot of things, what the standard has given the flexibility of the Mac layer, saying that you can take your own decision provided things has been configured to trigger and deactivate. I am giving you the provision. Say, for example, I give you one very good example called secondary cell activation, deactivation. I'll talk about what we call as a carrier aggregation. Now, why we do carrier aggregation? Simple, because of the throughput improvement. So it means that suppose this base station is configured with two such carrier, say carrier 1 and carrier 2. So we tell mobile that these are the two carriers are been configured to you. So but if the RRC activates the carrier, so what will happen? The device, his RF path, if you think of, it is on actually. His RF path is on because anytime the packet can come from the scheduler. But rather than that, if the scheduler decides that when I need to activate you, you have provisioned. Well, from the RRC, you have provisioned and make the EV aware. But to activate the carrier, it is on demand. So on demand, I will activate. When demand goes down, I will deactivate. Means I will activate the cell 2 and tell the mobile that I have activated you. I will start getting the packets. And then I flush out my buffers in my queue. And when my buffer is flushed out, I deactivate this cell actually. Okay, then what happens? It's best energy saving of my device itself, because now it's not the circuit is on actually. Now, based on my Mac element in the real time configuration, I activate, deactivate, activate, deactivate actually. So I'm saying giving some energy saving to the device. Okay, now this is the biggest things that we are trying to tell is that Mac scheduler, you based on your buffer, you take a decision. I have provisioned you from RRC. Take a decision to activate and take a decision to deactivate the secondary cell actually. So this is what the benefit that comes. So like that, there are a lot of things are there. If you think of the standard has given the flexibility, and who controls this, the timing of it. That is called the time control of this, this control elements. It is the scheduler who controls the activation, deactivation. Now imagine that if my trigger time is delayed. Now, what is the implication? Think of take this example of carrier aggregation. Your buffer is growing actually, and you didn't activate it to the device, saying that through this Mac control. So it will, and the buffer goes and it becomes the overflow condition actually. So I don't want actually to buffer to overflow actually, because you lose information. So rather than that, we have to trigger at the right time, so that I trigger the secondary cell through this Mac control element, dynamic signaling at the Mac layer, flush out my buffer, and then deactivate my secondary cell actually. So this is where the biggest thing that the scheduler keeps on doing it, that is that time to activate a secondary carrier to that user. If I activate it, okay, then when I deactivate it, because I don't want to activate it for long duration because it will eat up his battery life actually. So this is what the biggest things that where the protocol meets the scheduler actually, because scheduler is an algo. So the scheduler takes the protocol's help to do his job actually. So now think of he's now the data plane master actually, because if you see the packet flow, where all the packet get actually been buffered at this place itself at the Mac. Okay, so this is where if this entity delays the packet, now you can imagine the buffer will keep on growing actually. That we don't want, the growing buffer. If it is stalled, buffer will grow and it get into thousands of other scenarios, error scenarios. So there the scheduler needs some flexibility, and this flexibility is given through this Mac control elements by the protocol. So scheduler invokes the protocol, does his job, and gets the things done. and then he is done and he goes out in the other state itself. Okay, so this is the good part where we are talking about dynamic signaling handling at the MAC layer done by the scheduler itself. Another important aspect that we'll talk about that still goes with the MAC control called.
Sir, in MAC layer, like we cannot distinguish between the kind of data. Like you gave an example where you told a voice over NR and like the streaming data. So it comes from different logical channels, and at MAC they merge together in the buffer.
Correct. So MAC, what happens? Let me draw it for you. Suppose I have an user. So when we do the MAC configuration based on the user, say it has two such flows actually, or two such services. One service was voice over NR, and one service a high-speed EMBB kind of YouTube streaming. So at the MAC layer, we have the logical channel, what RLC will maintain, two logical channels actually. Okay. So what MAC is concerned about is that how many logical channels has been configured, because he knows that each of the logical channels has its own priority to deal with it. What he doesn't know inside what is there, but what we type of doing is that we try to do an indirect mapping, because voice data, this is known to the core network. Below base station, nobody knows what is happening. So what we do is, with respect to when the core network configures the base station, he doesn't tell you that what the quality, he only tells you what is the quality of service of this logical channels you need to worry about. Okay. Logical channel 1, logical channel 2. That is enough for me. Why? Because this person is actually doing the mapping between YouTube to my bearer actually. And that information is nothing but translate to the quality of service for that YouTube. And this is a high-speed YouTube. I'll show you one table. Just hold your point and tell me. So now comes to the quality of service is mapped to the logical channels. That is enough for me. Okay. And when the RRC configures the MAC, who knows this? This is the RRC person, because RRC has to also configure his own MAC, means base station MAC, and mobile's MAC also through our mobile's RRC. So RRC knows that what is the quality of service for that bearer that has been instantiated by the core network. And this is mapped ideally with respect to what we call as the QFI actually. Let me jump to the QFI very quickly, then you will come to know what this QFI means actually. Since you brought up this topic, I'll show you what QFI means. So at the end of things, I was trying to tell you what is quality of service actually. So what happens that 5QI is what the standard defines. Okay. So 5QI 1, 2, and each of this number, if you see, it is mapped by the standard itself called guaranteed bit rate traffic. And standard tells you that what is the default priority level of this. What is the packet delay budget that this has to, this 5QA1 has to deal with? What is the packet error rate? Remember, how many error of the packet that you can tolerate with? Okay. And what is the averaging window for doing your throughput calculation? And this is mapped to your conversational voice. You got it? Now what happens is that in the device, when you press your, say, suppose voice over NR application, okay. So your application in your phone actually tells to the NAS layer that I didn't mention. NAS is the first element who talks to your application layer via the man-machine interface MMI command. This application vendor, we knows that, okay, I am a voice application vendor. He tells to the NAS layer that I want to start on 5QI application number 1. So moment you say 1, the application vendor actually takes this table into account. Okay. Now this is known to the EV. Now EV's NAS will tell to whom? AMF. That is nothing but my core network element. Okay. So now core network knows that a user is starting on voice over NR application whose 5QI is 1 and whose bearer quality of service is to be defined like this. Okay. This is a standard table. So both the vendors knows, means anybody opens a standard, he picks up this table. So if he sends 5QA1, all these numbers he is known from this table itself. Got it? Now he will send to the base station now. That Mr. Base Station, a user is trying to start an application called 1, and this is his quality of service parameters. And this is I call as dash, means negotiated. Okay, with the device and the core network. This and this person can negotiate the quality of service beyond what he has defined. So he will tell the base station that this is what the quality of service has been defined. So this means that please start a bearer, that is my RRC bearer of this based on this quality of service. Who knows? The RRC knows. Now this RRC has two roles to play. This is a part of my base station logic. And this RRC also has to configure the EV that his own RRC, who will in turn will configure all the other layers actually. Now, who is here to configure? This is where the scheduler and the MAC resides. So he will configure the RLC that please start a logical channel with this priority. Then he'll configure the MAC that there is a quality of service of one logical channel of this nature I have configured. This is the internal configuration from RRC to RLC and MAC. So now everybody in the system is aware of it. Now scheduler knows that I have a logical channel of this priority number 20 that is mapped, because if you see here, you'll not find any replication. Okay, so it means that 20 is meant for this guy only. Okay, so he by default, indirectly, he knows that there is a voice over NR traffic that has been instantiated by the EV. Be prepared. That's the way I know from the logical channel values actually. Got it? So now the scheduler is fully aware of it. Now like that, another user comes, another say 5QA he wants to instantiate. So like that keep on happening. Now you have so many of summation of so many logical channels that are voice over NR, or maybe a conversational video, or maybe a streaming video, whatever IMS, anytime. Just remember that any application who is starting with this number, because this is the starting point. It goes from the user to the AMF, come back to the RRC of the base station, which configures his own MAC, RLC, and the EV. So the loop is all complete. So the scheduler is fully aware of that I have a voice or NR, though he doesn't declare like that, but he says that, okay, there is a 5QA1 application has been instantiated. Got it? That's the way the whole process works actually in the system. So everybody is everywhere is self-connected to the system. Now what happens is that clear?
Yeah, so like MAC is aware of the priority of the logical channels and what data it is transmitting. So does it maintain that many buffers?
Now, obviously, now the come is a fact that see a base station has to handle say 5,000 users. Okay, now 5,000 users, how many logical channels you want to configure? Okay, so we have to dimension because it's a hardware, right? I cannot have a supercomputer to run my base station. So I have to dimension based on my hardware, that based on my form factor. Remember, I talked about femtocell, metrocells, RRH, all that stuff. Different form factors of my base station will pop up. So I have to know based on my how much RAM. You see, if you go into software, it boils down to how much RAM you have actually. Now that RAM get partitioned to as a part of storing your buffer, isn't it? Because where your buffer will stay in the RAM itself, in one of the contexts. So if your RAM is there, so you say that this RAM I have provisioned for my one of that 5,000 users. Now how you divide this RAM for the first user? How many bearers? Voice over NR, or say ENBB, or what? So we defined these numbers that how many such bearers that the base station per user has to support. So if I say the base station can handle 4 bearers,
Okay.
so how many bearers we have? 20,000 bearers. Okay, now it starts the dimensioning of the bearer queue. Ultimately, it's a queuing theory, right? So every packet will come and stay in my queue. So now I say that, okay, this is my first user queue. This is my second user queue. And now this user queue, I'll further divide because I have 4 bearers, right? So I divide into 4 such values. Now this size, suppose this is a voice over NR. How much of voice on a packet I can receive? Say 132 bytes. So I can know that voice on NR is a latency sensitive. So I can define that, okay, I'll only buffer 2 such voice or NR for that user. Okay. Now this is a high speed YouTube. So I'll buffer a little more. That based on my delay or my scheduling. So buffers will keep on happening here. Now this is maybe another bearer. Based on the way of inflow packet, I define his size. So like that, you can define the total size. Say 132 into 2 size for your voice or NR storing. This size plus this size plus this size, this gives me the EV1 size of my buffer. And multiplied by, say, how many we have, we can define this whole. But where it gets stored in the RAM, as a software, you instantiate a memory and keep on associate that memory with one of the queue. That's the way the queuing works. So this is where we have to do the dimensioning of the bearer queue. This is called the queuing part of it, and how much of the traffic that I want to handle, how many bearers, how many users the base station will handle. All the stuff has to be dimensioned, and based on how much RAM you have in the system. It's a bit of software engineering merged with the cellular dimensioning concept. Is that clear? So this is where
so like now we have like 4 like buffers. So like the Mac would now take from one buffer which is higher priority, like from that.
No, that is his logic. We cannot dictate how I want to do scheduling. Now, I can only tell that this logical channel has a priority number 20. This logical channel has some priority. Now, the way the scheduler will pick up the users and its bearer, that is totally research dependent. That nobody can control between one vendor to another vendor. How he wants to clean his buffer. That is his logic.
Okay.
The standard gives you a guideline. So I told you, standard doesn't dictate your algorithm. It gives you a guideline. Whether you follow the guideline, you get some benefit. Doesn't matter that you have to follow 100%. So I can follow it my own way. But it only helps me to understand that the queue has a packet of a priority 20. That only I can able to get from the protocol, interworking with the protocol. That is enough for me. The scheduler stops at that point and does his own logic. That's it. Okay. Now, how you do the scheduling, that is very secretive and very his own way, actually. Nobody can dictate the way I want to do my scheduling. So here I have written called prioritization, priority handling. Now, how I do a priority handling, this is a standard slide. Now, he will not tell you that you have to do like this. Suppose I don't do my priority handling and I have some innovative way to handle my buffers. Fair enough. Unless until you guarantee a quality of service, that is fine. You got it. So these things, standard is silent. It doesn't get into this level, the next level. It remains silent, and it has to be, because that is where one's vendor product differentiates in another vendor's product. Okay.
Sure. Okay. Yes, sir. Thank you.
So let's move to the second point of the feedback. It is called the power headroom, actually. Now, what that mean actually? Now, just imagine that this is an EV, and EV as the standard based on the category of the EV, the standard has told that if this is the category of the phone, then it can transmit up to a max transmission power. And they have lowest one came out to be 23 dBm actually. There is another class called 26 dBm. So this is the P max, the power transmission max of the phone itself. Any phone vendor cannot transmit more than this. That is given from the hardware. Now what happens, remember the fact that suppose base station is here, the mobile is here, and the distance is say 1 kilometer. And there are a lot of reflectors here actually. A lot of scattering is going on. So what is the effect of the scattering? Your SNR will be low in the downlink. But what happens in the uplink? This in this base station, we can configure 20 watt, 40 watt. But what is this watt in the base in the mobile? It is only 23 dBm. Now, if it is a 1 kilometer, just imagine he's sending some, uploading something. He's uploading on say YouTube one video actually. So obviously his SNR is so low because the distance is high, SNR will be low. So it means the SNR for this packet to be received is very low. Or if you want to send some CSI feedback, remember I talked about CSI for open loop feedback. If the CSI feedback you want to send, his transmission power is low, then there is a chance that whether the packet will be received or not to be received. Obviously. So what is the ways I can increase? Obviously, there is another algorithm called power control we'll talk about. That helps to increase the power. But if you are saturated to this level, and if you are still going to 1.5 kilometers, then we cannot help it out actually. Obviously, the link will fail. And the packet, he'll lose the link, he'll lose the synchronization. Okay. Now, what is the power headroom means actually? Remember, this is an uplink CPO FDM transmission in the uplink. So we have the same grid. So in this grid, the mobile is being told to use some bit by the base station to send his data packet. This is what has been configured by the base station because other part of the grid, other users has been given. So this is for this user. Now, as a part of the OFDM concept, more you add the resource block, the transmit power get added up linearly. It's a summation of transmit power that is directly proportional to the number of RBs that you are trying to add up. Okay. Two scenarios can happen. One scenario is that you are at very farther distance, low throughput. To maintain a link, you have to tell mobile that please keep on increase the power. So then what is my headroom? The headroom means what is my maximum power of the user that can be configured minus the PSCH power actually means the data, it's a PAPR, keep on adding the power. So this is my headroom. So what is this? If you take 23 dBm, and if any point of time say this is my 10 dBm transmit power. So I have some headroom. So I can use this headroom in two ways. Either to come out from the any wireless fading of that transmission, because suppose the mobile is transmitting something, uploading video or some feedback is going on. So it can, the signal can fade. So I can use the power, the transmit power using the how much headroom I have to start not to fade actually, to overcome the fade using the transmit power. Obviously, my transmit power will not fade because my signal has increased, signal power has increased. So that can be one scenario. Or I can use this extra headroom to pack more RB, isn't it? Because I told it is as proportional to the number of RBs. Suppose I am doing a YouTube transmission that requires 10 RB, and I have a headroom. So with that headroom of power, I can configure say 15 RB. So what it leads to means more RB, more information that get exchanged, isn't it? So this is where I start benefiting to use my power headroom. So this power headroom is most essential that the scheduler wants to know from the device. Okay, so he can use this one to pack more RBs, pack and mitigate the interference, pack my right MCS, a lot of things he can use to use this power headroom up to a point of maximum 23 dBm. Okay, so this is another important element that the base station, when he's trying to actually act upon in the uplink transmission, this is not in the downlink, by the way, this is the uplink scenario, where based on the uplink, where you are at a larger distance from the base station in an uplink SNR is bad. The power headrooms helps to circumvent the channel effect or bundle more RBs, more throughput, you start getting into it. So scheduler is every time polling the device that please send me your headroom, please send me your headroom. Okay, so moment you get the headroom and how the headroom comes, this is what. Okay, so how to see, this is one MAC control element called entry of the multiple PHRs actually. So this is the power headroom report that the mobile sends to the base station through the MAC control element. So this constantly updates the scheduler. See, now see the scheduler, he started tracking you with respect to your beam, with respect to the channel state downlink information. He's now tracking you with respect to uplink sounding reference. He is now tracking you with respect to your power headroom. We'll see, keep on adding more and more as we go along. So he's now tracking you with respect to what I talked about is called the scheduling request. That are you sending any scheduling request? Okay. So from the scheduling request, he's interested to know what we call as the buffer status information from the device. Remember, device is also sending informations. He has informations, right? You want to upload a video, you want to do an FTP, you want to do anything. So in your queue, based on what you wanted, remember that 5QI mapping actually. So you are supposed to send in a uplink direction some information. But how does a base station know that how much information you have stored in your buffer, in your queue? Because this is where this report is being sent to the base station from the device to tell you that what is this list is very long list, but it tells you each of the index that what is my byte that is expected from this value itself. So moment I get a value, the scheduler knows it. And how I get the value, the trigger first comes from the SR scheduling request. Means if the EV has the buffer, he will ping the base station with SR actually scheduling request. Moment I see a scheduling request coming from EV, I know that the EV has a buffer. But then now the question is that if I don't get your actual buffer information, then I cannot give you the right grant. It means how many RBs are required, what is the right modulation I have to give it to you, how will I know? Then he'll ask the device, please send me the BSR. And the mobile will send the BSR, and this is what he'll send it to the scheduler. So with the BSR, with this table, I'll come to know that how much of the buffer this user is expecting in his queue actually. Okay, and this is buffered based on not the full logical channel, but it's a group of logical channels. And this group is again done by the base station itself. And this group, we can take it into varieties of different ways. And based on the application service, we can form a group and tell the mobile that based on your group, report me your buffer. And this is what the scheduler is interested to know every time. Okay. Now we know that scheduler has sent a buffer and we are transmitting the informations actually. Now the biggest problem of the transmission is the reception. It means suppose I send the packet and somehow the packet has error and the CRC didn't pass, negative CRC. So it means there is a block error rate defined actually. So we'll discard the packet. So moment I discard this packet, I'll not discard in the sense logically, I'll keep it for my doing some other stuff. We tell the base station saying that there is an arc of NAC, negative acknowledgement for the packet that you have sent it to me, actually. Okay. Now what the base station will do, he can ignore this total feedback. And he can proceed and keep on sending that part. That is not right, because remember the flow of information is top down. So one of the packet in that whole structure loses out. You loses that information when you try to render in mobile's application layer, because mobile's application layer, how it works is also in a sequential manner. Like first packet, second packet, third packet, it goes in that sequence, right? So in one of the packet is lost and get into arc, and if it is not retrieved, then if you think of, there is a jitter blur that has been created, and that creates the complete application packet rendering. Render means you're rendering in your application not in the right manner, because you don't have information to it. So you can see all the blur in the screen, right? Some sketchy things start coming because there is no information that mobile does have for that packet. So what best you have to do? I have to do my retransmission. And this is what the scheduler is tracking it out, that my last packet is ACK or NAC. If NAC, I have to retransmit very quickly, because before the sequence of my RLC is broken, I have to keep on making sure that this part of the packet is successfully delivered to that. Now, if not delivered, then some other guy will take over. So this arc is another big problematic scenario that lowers your throughput, actually, because this is unnecessary transmission. Because the channel, you are bound to do that. But due to this boundness, what will happen? Your average throughput starts falling, because you are not sending any more information. You are hogging the cellular resources. But just to ensure that the packets successfully get transmitted, and the device use the incremental redundancy to combine the packet and make sure that CRC passes or CRC become positive, actually. Means it's a positive CRC, means the packet can be rightly delivered back to the MAC to RLC in its order, goes to the device application layer. Now, how many such retransmission, what we call, can be provisioned? Okay, so the standard has very high value. Now just imagine that if you have gone with a typical retransmission 4, so whenever you start getting NAC, you retransmit. So one of the retransmission 1, second, third, fourth. So this is the way you try to ensure that at some condition later, the MAC or the device comes to the favorable channel condition and able to use the incremental redundancy combining technique to get the original packet done, so that CRC get passed out again. Okay, now this is what the scheduler is constantly tracking it out. Now what happens?
Sir, this concept is a blur concept, no?
Come again?
This is blur you are explaining, blur concept?
No, this I'm explaining the implication of arc when you get into the CRC failure, actually, or the blur comes.
Yes, blur, actually in blur also, beat error rate correction, we are doing the same thing, no? We are just checking whether NAC is coming or not. And the same number of repetition.
Okay, let's do it in this way. MAC doesn't work in bit level. MAC works in the block level, actually.
Okay.
So physical layer works in the bit error. When we do a bit error SNR curve, it goes in that order. But the MAC, because remember, it is all segmented that has happened, actually. So he is getting block by block and try to do the CRC check on that block. Okay, so his block error rate percentage, typically we take the target block error rate. So every operator, based on the service, he may choose to define this block error rate for that service. And that is happening at the MAC level. Okay, but how the blur get calculated by the MAC? Based on the packet he has received and seen the CRC, because CRC physical layer will calculate the CRC and tell the MAC. Then MAC takes a decision, oh, it's a negative CRC. So it means that the block is errored. Oh, this is a positive CRC. It means that the packet is successful, the block is successful. So then he calculates the block error rate actually. Now, what is the block error rate typically value? Say 10% block error rate you can think of. Okay, so one of the 10 packet is error actually. So that way you can think of the block error, not the bit error. Error happens at the physical layer level, that what is my bit error that I want to deal with it. But at the MAC level, we are concerned about the block actually, because now we are trying to define as a packet. So summation of bits becomes a block or a packet over which we have to see the CRC, what is happening. Now that happens post your LDPC decoding has been done. Okay, so that is the beauty of the block error rate, where we are dealing with the packet level actually. And if that block error CRC is NAT, means CRC didn't pass, then we start in telling the user that I'm retransmitting the packet, and this is my redundancy version that you please use for your transmission actually, for doing the combining actually. Now, how many retransmission we want to go for the things is configured. The standard gives you large number from up to 16. So you can decide that what is your best option. You can go with 0 also, means that if it's MAC, throw it, move forward. Just imagine a voice packet, if get into HARC, how difficult the garbled voice will be actually. So there are certain services we don't prefer retransmission. Lost is lost. Okay. But there are certain services we want a retransmission to happen through HARC actually. Okay. And what also we try to do it in the HARC is in 5G, we started defining the HARC process. So each process we associated with one of the transport block, and they can deal the HARC in their own manner actually. So nobody stops, means scheduler doesn't stop. He keeps on putting the packet on one of the HARC process, so that each HARC process deals with his HARC independently actually. Okay, so that's things that the HARC mechanism works actually in this order. Now, the combining is a physical layer activity, but the controlling of that is the MAC layer activity or the scheduler. Okay, the controlling portion of it actually. Okay, now this is what.
So what if if Mac takes up a takes up a packet from a buffer and it directly performs 4 to 16 repetitions on that instead of waiting for HARC retransmission?
No, see, repetitions is done in another separate feature point of view, where we do the bundling. Okay, like we bombard. Okay, now what are the implication of it? Suppose the user is in just say 100 meters good radio condition. Does this bombarding make sense? Because one packet itself without HARC he can receive, isn't it? So scenario to scenario, the scheduler actually tracks you that do I require to bombard or do I go with a HARC mechanism? So this is also a runtime decision of the scheduler. He doesn't want to bombard 4 packets instantly because there is no point. Unless I'll be hogging my resources. Remember, every resource will show you is a costly from hardware, software, everything. If I get into a HARC or I start bombarding 4 transmission one shot, one by other, if he in a good radio condition, why I want to do it? It's unnecessary for me, isn't it? So these decisions are the runtime decision. Scheduler takes in one slot level that click, I want to go with the logic of bundling. Click, I'll start getting into HARC with this user for this service. So in that click of that slot, he takes that decision logic. And that logic you have to build and write that logic because it doesn't play, it's not like automatic. We have to have that mechanism, software, simulation, algorithm. This all governed with the algorithm that to take a decision by the scheduler to start taking that decision runtime on the fly. And this is happening on the fly, by the way.
Okay.
Got it?
Yes, sir.
So that's the reason the channel information is the greatest asset the scheduler has it actually. Because from there, he comes to know that what decision I have to take for that user. got it, to not to go into HARC or drop it out or go with a bundling scenario is a runtime decision that needs to be taken into account. But this is a major, what do you say, entity of your scheduler, that how I deal HARC of so many thousands of users in my coverage area. Got it? So
Yes, sir.
the question that I'm posing is that what is the ideal value of this HARC? Okay, so do I configure 0? Do I configure 4? Do I configure 8? Or nothing? How I configure my HARC for you actually? So this is a very simulation-centric, decision-centric logic that we need to start taking. Now we'll put all these blocks once we form the scheduler in logic. So let's take another important part is called link adaptation logic actually. Again, the scheduler is involved into this logic actually. Now, what is link adaptation logic? Now, remember in the standard, this is the modulation or the MCS value that the standard defines in 9. So moment 9 comes, I talked about that what is the efficiency, what is the coded and all the stuff happens. Now let us take a scenario that a base station in his very near, then somewhere some another coverage, and this is the lowest coverage, maybe a cell edge zone. And this is his cell-centered zone actually. Maybe this is one the mid of the cell edge. So what the scheduler does, suppose based on the CQI, remember the channel quality I showed you, he decides come to and choose one best MCS for based on that CQI, and he choose that MCS logic. He tells the user that this is what the packet will come with this modulation on the code rate. Okay. Then I expect a feedback from the device, and device gave me a NAC actually. Okay. Then what I do, based on the NAC, I'll get into the retransmission logic actually, then that is fine. But now just imagine that I get into the acknowledgement actually. So it means that the scheduler starts becoming greedy from the link point of view. Greedy means that if he thinks that if this MCS is passed with an ACK, then can't I increase with the next step with another MCS? Why? Because I may send little more information to it. Suppose I get another ACK for this packet, for this MCS, then he becomes still greedy to get into the next level. So now you can imagine that the mobile is standing at one point or whatever. So based on that, the ACK, the mobile is actually MCS is going up and up and up. You can go in this order. Obviously, there is a point in which it will again break. Why? Because as a part of the basic wireless physics of the transmission, the link of the right power cannot sustain an MCS. There will be some amount of MCS he can go, but beyond that, he'll start getting the blur and the NAC. Now imagine a scenario. I talked about a sunny day scenario where using the logic where we are increasing his MCS one by one actually. Now what happens that you had NAC and you had 4 NACs actually. Okay, so your packet is gone and mobile is not able to retrieve his packet. Now you decided that, okay, I want to send another new packet. Now I am a little conservative now because last time I got 4 NACs consecutively from the last 4 transmissions and none of my 4 retransmission were successful and all were NACs. I was standing at here at MCS 14 and what got into NAC. Now I start becoming conservative. I go down here or I down, how much down? That is my logic. Now I'm reducing my MCS. So I'm started becoming conservative. So with the ACK, I can become aggressive. And with the NAC, I become conservative. Conservative in deciding my MCS. So this procedure happens constantly. ACK, NAC, ACK, ACK, NAC, NAC, ACK, NAC. continuously the scheduler is monitoring actually. And this procedure is called the link adaptation. Got it? That happens both in uplink and in downlink. So through the link adaptation, based on his previous ACNAC status, I may become conservative in giving MCS or I become aggressive in giving MCS. Got it? So the question is that now, so when you schedule a packet, you get ACK. Now let me put it the question like this. Suppose this is my time T0. I schedule the user at say 5th millisecond from the time. This is where the packet has been sent. I got a NAC here. And from this time, the scheduler didn't schedule at say at 60th millisecond, I picked up this user number 1, say V1 for scheduling. Due to some reason, I didn't schedule till 60 millisecond from here. Okay, now last time I got a NAC. Now what will be my MCS here? Because 60 millisecond is quite a large time. And if you go with the mu1, you know how many slots that is 120 slots. So after 120 slot, we are scheduling the user. I have a history of his NAC earlier. So what MCS I go for? Whether I go with conservative or I go with aggressive? Because it may happen his channel might have gone up, or it may happen the channel might have either gone down. I don't know. So this is called the traffic pattern, that if you schedule the user based on his low throughput, based on his scheduling delay issue, or your algo is not right, your history of your things is very old. You cannot take any decision actually. Your decision, you can take a decision, but your decision is not right decision. You may hit with that MCS conservative, you may hit, then your throughput will fall. So you have to recover your throughput. Remember, your buffer will grow. But if you become aggressive, you may land up into the hark again because his channel never improved. So this is very, very important decision, that if your traffic pattern means if you have a pattern of traffic that is coming very slowly from the internet, okay, bursty traffic, very difficult to deal with the link adaptation for a bursty traffic. But if the traffic comes regularly, it's good enough because I'll keep on scheduling, get the feedback. But if it's a bursty traffic, once in a while I get a big packet and my feedbacks are very old, I don't know what basis I'll take the decision of my MCS. Okay, by the time the decision might be the channel has varied, your modulation and code rate or rank might have decreased or increased. You don't know, anything can happen. And more bigger problem that if you are getting into handover. Because suppose I trigger a handover here, I don't know what will be my after handover, what MCS it will start off actually, because handover happens at the lowest RSRP. So this is where the problem of the link adaptation we have to think. And it is the biggest problem to ensure that link adaptation augments scheduler in deciding his MCS. Because what the scheduler takes a base decision that, okay, based on my CQI, I map to this MCS table. I know this is my MCS, some number I have to take. But then what happened? I call up link adaptation, saying that, hey, link adaptation, tell me that this number is fine for me or not, because you are tracking the hark earlier for this user. So can you correct me this number? And link adaptation with the help of link will correct this number as much as possible. Okay. So this is another big things that it is a fall under the purview of the scheduler through link adaptation to rightly decide and don't want to get into the NAC. And suppose I take a decision that I become every time conservative, then I become, my throughput falls down, my buffer goes up. That is also not right. So I have to be sometimes conservative, sometimes aggressive. What point aggressive, what point? This is the big decision of the link adaptation logic. and where this logic feeds into back to the scheduler again. Okay, let me go with another problem statement. And this problem statement is again the uplink problem statement called the power control. And I talked about power control with respect to the power headroom actually. So the standard normally gives me that if you have a data from uplink to send from device to the base station, standard is a standard equation. But the standards actually tells me that you can have the provision to control actually. There are certain things that it is under you, what we call as the transmit power control command. And this command, I can increase, decrease my power with this amount of dBs actually scale. Okay, it means that the scheduler can tell the device, next time when you send a packet, please increase with -4 dB decrease, or you can increase with 1 dB or 4 dB based on what is the configuration I have my power control has been working. So now the question that comes here is that when to send this power control command to the UE? Because remember, if you keep on sending power control command, you will hit the 23 dBm max transmit power, and your power headroom size will become 0 or negative. So I don't want to unnecessarily increase the power of the device, because if you unknowingly start increasing it, remember the big cell deployment. This is the base station. This is the coverage area. This is the user. But there is another base station who has its own users that are there. Now this, when you are increasing the power, there is an interference from this is getting created here. You're actually causing interference. So more power, more uplink interference. And if it becomes as a cell edge guy, so this power will be picked up more easily by the other neighbor's cell actually. So you're hitting the interference. So how much of the transmit power to compensate the uplink interference? So you need to increase the power, but by how much? And also you have to ensure that if you keep on increasing the power, remember the physical layer is also a software. It gets into the saturation actually, it might get into. It decreases your amount of battery life, because your mobile is constantly draining the battery for 23 dBm transmission. So is that only to be used to maintain the target blur in the uplink? So why I have to increase the power? What for? Can't I do with link adaptation? Can't I do with other mechanisms? Can't I do with reducing my rank of my transmission? Why I have to use uplink transmit power? So this decision is very, very dynamic in nature. So the scheduler sometimes take link adaptations, sometimes he'll invoke the power control and then decides that what to be done actually. And it is slot to slot, slot to slot, the decision can vary. He may decide that, okay, let me few slots, I'll use power control. Then he may totally stop. So this is what is the constant mechanism, and the questions that the scheduler, what I'm writing the questions is actually the scheduler is thinking slot actually. When he thinks at that level, there is a logic for him to think at that direction, that why I have to take which path at what point of time. So if he's, then I was talking about that a good scheduler is a bad scheduler. So if these logics are not taken care holistically, we do simulations, but what will happen, these, you can understand the gamut of making a mobile stay in a coverage area. That itself is a humongous task for us actually. We normally crib saying that, oh, I'm getting into buffering, things are not good. But just imagine that in the background, how complex these mechanisms are working that affects any wrong decision by link adaptation is a costly for the scheduler to run for the next few slots. You may get into buffering or a link failure actually. If you increase your power too much, uplink power, you create an uplink interference in some other cell unknowingly. So people in the other cell will worry that how come I am getting more interference, from where the interference is coming? Is that a TDD frame format problem I am getting, or I'm getting through maybe a neighbor EV been blasted with the highest power. I don't know. So this is where the dilemma goes actually from the scheduling logic decisions. Okay. I talked about the another logic called the carrier aggregation. So I want to leave this point stating that the activating the carrier and deactivating the secondary carrier is very time sensitive and time critical also, because more time you remain activated, it is a battery drain of life. Though base station has an energy problem, that is its own problem, but the device are in battery. So we have to handle the device in very, very careful manner. So carrier aggregation is where we try to add more carriers just for the throughput gain. Okay. So that helps me to give more throughput unknowingly to the users whenever we see a more buffer. So I have a primary carrier and can keep on adding carriers to get my throughput actually. So this is what the way the things get function. And quickly with respect to the millimeter wave, again, see the gamut of the scheduler that is moving actually. So if this scheduler, apart from doing all other stuff, if he's meant to be working for the millimeter wave, so he has to ensure the beam tracking, the beam management aspect of it. So he has to ensure that how my beam pattern, which beam to send, how my analog beam width that I have to configure to my RU, how sharp the CSRS beam needs to be, how many neighbors beam that I have to manage. This is his problem. If it is the scheduler, same scheduler, whatever he's doing for that one, plus you have given an extra headache saying that you are now a MMF and you have to do the beam management. So see the another dimension that got added to the scheduler. I'll skip this one. I'll spend a little bit of time here on the scheduler. Now you can imagine that the scheduler logic, when we build it, unless we think that's a good scheduler, think that how much gamut he's trying to think over it. I talked about with respect to the MCS. I talked about with respect to BWP switching. I talked about the pre-coder part of it, the carrier aggregation, HARC handling, the CSI handling. Then we have the digital weight, link adaptation we talked about, quality of service we have to prioritization, power control we talked about, millimeter wave beam management. And if it is a URLCC, he has to manage the URLCC slot scheduling. He has to manage the signaling that is coming. It's a huge, huge entity. The scheduler has to be done. And top of that, he has to be fair enough. Because I cannot be unfair and say that, okay, I'm loaded with very few typical aspect of my users in my cell actually. So now you can imagine such a big dimensions that when we take a decision logic, the decision logic, you can think of how much it influences. And one of the logic is not properly giving me the feedback, say link adaptation. You can imagine that to correct a wrong decision, the quality of the user suffers actually. He experiences very bad quality actually. So this is the main gamut of our layer 2 from the scheduling point of view. Okay. I just rushed through very quickly because of the time constraint I'm started getting into. So I talked about the data flow. So I talked about that IP packet. Each of the protocol entity adds a relevant header. And this is the total size of the transport block that gets to the physical layer for that user itself. Okay, so a lot of things that it has to deal with, and why I do all this segmentation, we'll see it now. Now let me get into the next protocol layer. A little bit of rush through now actually because of time now. So we are into the next protocol layer called radio link control actually. So radio link control sits above MAC and below the PDCP layer actually. Now why we have kept it? Because fundamentally before HARC came, the retransmission mechanism was done through this ARQ mechanism. Okay, before the HARC concept comes, so the RLC was trying to do the ARQ, automatic repeat request. He has to do this kind of HARC. Hybrid ARQ came at the MAC level. So now in the network, we enable both HARC and ARC actually. Now, if ARC fails, ARC in RLC takes over for error control mechanism actually. So he'll do the retransmission and all this stuff. So if that fails, then nothing. Then it is a TCP. If it is a TCP or if it is a UDP packet, lost actually. But if it is a TCP packet, then TCP retransmission will happen. So that's the way the whole sequencing has been done. And RLC is the person who is very important because this is the person who actually does the segmenting of the IP packets. Because remember, your physical layer, resource elements is very costly because of the spectrum. I cannot in a slot give to all the spectrum to one user. I cannot give him 1 Gbps to 20 Gbps. It is not necessary. So I have to segment the packet at what layer. Mac, you have seen it, how closely he's working with the physical layer. He doesn't have no time now to segment the packet. So there is this entity, the RLC, who does the segmentation of my packet to benefit Mac layer actually. So if the base station does the segmentation, then the mobile will do the reassembly. If the mobile does the segmentation, then the base station will do the it's just opposite. I told you the peer-to-peer stays actually. And another big thing is that Mac just transmit the packet and do the ARC. But remember, in the system that it can get into the duplicate packet, that Mac is not aware of it. Because who puts my sequencing of the packet? And this is the person, the RLC, who does the sequencing of the packet numbering actually. Okay, so he puts you the sequence number 1, 2, 3, like that it goes. So the first sequence packet will go to the Mac scheduler actually. And then it will do something on the transmission. If successfully done, then done. Then the second packet will go to the Mac.
Sir, I have one doubt here. So the sequence numbering, will it come after segmentation or before segmentation itself? It will be sequence the packet.
So the segment, see okay, let us do the segmentation. Then you can. This is the IP packet. Okay, now this IP packet, again, if you think from the IP packet, there is another sequencing that the PDCB layer will do. Okay, let me put this guy first actually, then you'll come to know. Now you got 1500 bytes of packet from the IP layer. Got it? So the first thing is that the PDCP will put one sequence number. He'll put one sequence number to it. Now this packet now goes to the RLC. Now let's go back to the RLC. So you have one sequence number that is put it in the header itself. Okay. So now the RLC gets this packet, sequence packet, PDCP sequence number packet 1. Now RLC got this packet. Now what is the size of the packet? It is still 1500 bytes of packet. Okay. Now what I have to do is that I have to break the packet because Mac works with the lesser packet because of the nature of the RF. He will tell that please segment. Now I'll segment it out. Now each of the segment RLC I'll put 1-2-. But this 1-2- packet is for the PDCP sequence number 1. Got it? So this segmentation is what the RLC augments your Mac to make a smaller packet, and that we have to track it out. This RLC will start tracking his own sequence number packet. Got it? So there are two sequences that the whole sequence that flows through the packet lifecycle. The PDCP, when he receives the IP packet, he has to ensure that when he forms the final IP packet from the RLC, he has to get the proper 1- plus 2- plus 3- to get me 1. This is PDCP sequence number. But RLC maintains his own sequence to augment the Mac based on what he wants to transmit to the layer 1. Got it? So now the question that comes here is that when you sequence it out, you have to do the desequencing. Means you have to put your concatenation, resegmentation, everything in proper so that you get your sequence packet out in that layer itself. And this is the only role that still we are trying to keep it at the RLC level, and that can be merged in future standard spec that, okay, why you need PDCP now. If I jump back, okay, before I jump back to the PDCP. So there are two types of transmission that the RLC deals with it. One transmission, what we call as a transferent mode actually, where there is no header that RLC starts putting into it actually. So typically, if you think that there are certain logical channels that RLC is not bothered to put any header to it actually, that goes transparent to the RLC, because this is the information directly comes from the RRC actually. So he doesn't want to disturb and do the sequencing and all the stuff. Straight, it want to send to the MAC. There are other modes that called as the UM mode actually, and the acknowledge mode, AM mode actually. So based on scenario to scenario, that this UM and the AM get associated with. So typically any dedicated control message, like RRC wants to send it to the device. So then we use the UM mode of the transmission part of it. Then if there is if you think the downlink traffic actually, now that we want to can go with either UM or AM mode. So if it is AM mode, this is where the MAC, the RLC, not the MAC, it get into the ARQ actually, because there his duty starts coming that whether I'm getting into the ARQ mode or not actually, because once he get into ARQ means the HARC has failed actually. The HARC retransmission of so many times has failed. So I have to take over that part of the decision actually. So now the decision is that does all the DTCH packets get into AM mode? The answer is no. Now why? Because for example, you have an application layer that is sitting in internet, and that guy is already a TCP application, you know actually. Now suppose you put him in the RLC AM actually, so that goes into ARQ. So it is unnecessary retransmission actually. Because why unnecessary? Because TCP has its own capability to do it actually. Why I want to do it? I can safely put in a UM mode itself. Okay, so that way straight away that application layer can deal with it. I am become little free from that actually. So there are certain things we take a decision based on what is the service, which service. Because remember the service is associated with your 5 QI and that is sitting on your logical channel. So which of my service actually needs what RLC mode of treatment, and this is all operator. It is nothing, any rule is there actually. Operator decide that, okay, I want this service in my network to be going as RLC AM mode. That's the decision, his policy. I cannot tell good or bad. He can change his policy seeing the performance. Okay, so he can decide, okay, I am deciding of this service get into the UM mode. Fine, it is his policy. He doesn't want RLC to run. It's better for RLC because he doesn't get into ARQ mode actually. So there are certain things that we have to think of, that operator decides that which service. We ask the operator that, do you want this service to be RLC, which mode that you want to get into. Especially the contention happens between AM and the UM mode actually, that which mode is the best mode to tackle with it. Okay. So I stop at this SDAP because I want to bring that the flow actually, then you'll understand why this SDAP is required, and how we say flow with respect to the service and with respect to the IP packet. There is a nice slide is there. I will stop at that point and do the flow mapping. And this is a new entity that got added, where the bearer, so remember the bearer is dealing with at the MAC level. So how many bearers we're trying to put forward, what if it is a pipe. Now in this pipe, which flow is mapped? This is important for me, because now I'm giving a guaranteed bit service for this flow, sorry, this bearer. But if I'm not sneaking into every such flow to flow, and that is humongous, because so many flows I cannot deal at the scheduler level. You have seen it, the scheduler, how much complexity he's dealing with actually. Top of that, if I tell that please go into and see the flow, then it is humongous task for him. So we try to map a bundle of flows to a bearer actually. And then we say that scheduler, this is what the quality of service of that bearer is being negotiated with the device. So please adhere to this quality of service, this commanded given by AMF to RRC of the base station. And RRC then configures the scheduler that this is what the quality of service for the bearer to be given. Now, within that bearer, how many users flow has been mapped, that will see the trick, that how they try to do it actually. Because that is where he is trying to offload some of the unnecessary stuff in the scheduler that happened in the 4G. We try to abstract it out at the bearer level and then deal in a separate level at the flow. Because if my mapping to flow to radio bearer decision is wrong, then obviously I cannot help it out because I'm giving a quality of service at the bearer level. So this is a very important decision, that how we map, what ways and means to map it out between flow to the bearer. And this is not governed by the standard. This is what the operator, he thinks from his previous experience of his network traffic flow actually. Okay, so let me come back very quickly. I talked about what is this PDCP layer. So one of the things he does, the IP sequencing part of it. And the biggest things what I will say is this entity called ciphering and integrity protection of my packet actually. Because this packet, when it enters, if you see from the top in the data flow region, so above your PDCP layer stays your SDAP. So here you get the packet. So this packet has to be encrypted actually. And after that, RLC doesn't know what has happened after that, after encryption, because he thinks bits are coming. So he thinks that is my packet for me to it. So the biggest thing that happens is the sequencing it out, the IP sequencing. And remember, and this is what the ciphering and the integrity protection of your packets actually. Okay. Now let's see that what is left out actually is that my whole network is protocol wise is governed. I have still one more to go called the radio link part of it. So I'll go just quickly that if you see in the hierarchy of a base station, actually, if this is my base station, the complete entity now, at least one, we are talking about the MAC scheduler at lowest level. But actually, if you see in my top of my hierarchy of my decision making, if you think of who is my prime minister of my base station, this is what this entity is, my prime minister of my base station. Okay, because this is the person who actually provisions scheduler. Now, till now we have talked scheduler to take a decision. That is fine. But if the scheduler is not provisioned with the right by the RRC, then the scheduler cannot work functions efficiently. Now, how does RRC behave? So RRC does what we call as a P11 selection. It does the broadcast information. He does the cell selection in the idle mode. He augments in the paging. And we divided the RRC in the 3 states of the RRC. Okay. So in till 4G, we had 2 states. Now we added another state called inactive state. So state changes like this. It can go from idle to inactive to idle to connected. There is a well-governed state mechanism, and each state, what the standard tells you that when you are in that state, do that job actually. So it helps us to write a software that based on my RRC state mechanism for that user, I have to do this part of the job, that part of the job actually. So it is more organized. Now you can think of a top central entity who is more organized to take one decision at based on what state of my RRC. Now, what decision it will take? Let's see that what decision he has been empowered to take it. Now, he has been empowered to configure the system broadcast information actually. Okay.